Welcome to this video series on design patterns in Java. In this video series, I'll take you through the world of design patterns. What are design patterns? We'll look at the history of patterns. We'll contrast patterns to some other things like idioms and analysis patterns and so on. And I'm going to cover 15 of what's called a gang of 4 patterns. These include things like composite, proxy, adapter, and decorator, and so on. That's 15 out of 23 patterns, and I try to use the most commonly used patterns. And the goal for me here is to make sure that you understand when to use the pattern, understand how to implement the pattern in Java in particular, and also being able to contrast the patterns. The Java here, I'll come back to. Java is the language that we've selected to use for our examples. Before I teach the patterns, let me give you some context to the design patterns world. What I'll cover in this chapter is the history of design patterns, what is a design pattern, patterns versus idioms, and look at some of the various abstraction levels that exist out there, various specialization dimensions for patterns, and we'll look at the pattern's role in building advanced architecture, and also give you some suggestion for how I would go through this course if I were you. Let me first tell you a little bit about the history of design patterns. And I want to start back in 1977 and 1979, where this guy, Christopher Alexander, wrote a set of books on architecture. Not software architecture, but buildings. And he wrote one book in 1977 called A Pattern Language, looks something like this. He wrote another book in 1979 that's called A Timeless Way of Building. Two great books about regular architecture, but what was unique about these two books is that it described the style of how to describe architectures, because often architectures are ideas rather than very concrete solutions. So his ideas could be, for instance, how do you light up a dark corner? Well, there isn't a single solution for that. There are many different ways. And maybe you even want a dark corner and you want that as a place to read or to relax, for instance. So he came up with this idea of describing what he called patterns in architecture. And he created also a concept of a pattern language, which is a sequence or a set of patterns that work together as a language. It could be some kind of flow if you want. So you make a decision, is this a good solution? If not, here is another solution that you could try. So it's a set of related patterns over some topic. And nothing really happened related to this in software until Kent Beck and Ward Cunningham in 1987. Kent Beck is probably more known for his work on test-driven development, for instance, and Ward Cunningham is probably more known for his creation of the wiki. In 1987, they came together in a UPSLA conference. UPSLA is a big conference on object-oriented technology. They came together and tried to use the concept of pattern language in that conference. And it was probably one of the first known places where the use of patterns or pattern styles were discussed. That was in 1987. At the same time, a gentleman called Eric Gamma was working on his PhD, creating a framework called ET++, which was a drawing editor. He was interested in the object-oriented patterns that he found when he built this system. He felt like there was a set of reusable constructs, and he wanted to capture those. So in Uppsala in 1990 in Ottawa in Canada, there was a bird of feather session arranged by Bruce Anderson, where Eric Gamma and also another one of the Gang of Four and a set of other people started to seriously discuss cataloging these patterns. In 1991, Eric Gamma and Richard Helm on a rooftop in Zurich before a ECOP conference were creating the first known catalog. They were trying to bring together the patterns that they agreed upon. This first catalog contained some of the familiar patterns that we know today, like composite and observer, but it also contains some patterns that never made it into the final book. And those are patterns such as the constrainer and the decider, for instance. Later on that year in 1991, Uppsala came around and Bruce Anderson had a workshop, and that was the first meeting of the Gang of Four, as we know today. as Eric Gamma, Richard Hill, Ralph Johnson, and John Lucides. It was at this workshop that the Gang of Four started to work together towards a manuscript where they would publish this design patterns catalog that finally came up in 1994. Well, I should also mention that James Coplin came out with a book called Advanced C++ Idioms and Styles, which was some work that he was doing at AT&T to teach people how to use C++ properly. And there are a lot of people that feel like this was one of the first books on patterns. But because it was focused on C++, we often think of these language patterns as idioms. So it probably hasn't quite gotten the credit that it deserves. But that also happened in 1991. Now the ball was rolling and a lot of work happened. There were various meetings, a lot of friendly discussion. And I happened to get involved sometime in this period because one of my consultants when I was a software manager at the Dresser was a guy called Desmond D'Souza, who was very involved with this. And we used him as an object-oriented consultant, and he later became my boss when I worked at Icon Computing. And he shared some of these ideas with me and gave me early manuscripts of the design patterns book, which got me really excited, I have to say. And finally, late 1994, the book came out, although there were a lot of people that had access to the early manuscript and had had a chance to comment on the early manuscript. And it became one of the bestsellers on design patterns. And it's the book that I'm going to put most of the emphasis of this course on. Since 1994, there has been a ton of books that uses patterns because patterns sell, and whenever you see patterns on the book, it seems to sell better. But there is also other reasons. People try to apply patterns or use the pattern style to describe various things. So you had things like, say, the JEE patterns or the J2EE as it was back in the days that was written. Martin Fowler came out with an excellent book on analysis patterns, where he looked at patterns being used when writing requirements, if you want, sort of object-oriented modeling patterns. You had enterprise integration patterns, and so on. So the word pattern is now used in a lot of contexts as a way of describing architecture or different solutions to implementations. I think the Gang of Four book has opened up a path for how we describe certain ideas in software. So just to summarize the timeline, in 77, 79, Christopher Alexander wrote these pattern language books for architecture, which is where Eric Gamma and the Gang of Four went back and got a lot of their inspirations for how to describe things. 87, Beck and Cunningham had this pattern language for software sessions at Uppsala. But it was in 90 when we had this bird of feathers session on patterns, and in 91 to 94, we got various collaborations on defining patterns, particularly by the Gang of Four. And in 94, the main book on design patterns came out. And since then, numerous books and initiatives around the concept of patterns. Now, if you have never heard of a design pattern, you might wonder at this point, what is the big fuss about? So a design pattern is a named solution to a problem in a specified context. And that makes it some kind of reusable design knowledge. It's object-oriented, and its name is very important because it allows designers to refer to it. And that increases the bandwidth of communication, if you want. There are no standard for how you describe the patterns. There are multiple publications. Each one come up with their own way of describing the patterns. And most designers will refer to the Gang of Four patterns as the groundbreaking way of doing things. So when we describe a pattern, at minimum, we have to give it a name. And the name, as I said, important for the bandwidth of communication so we can refer to it. We have to describe what problem it's solving, and typically also in what context of interest. And then it would have a given solution for the problem in that context. And that's really all it is. So we're trying to describe something that is reusable, that we think might be applicable in multiple settings. Eric Gamma and company, or the Gang of Four, learned from the Christopher Alexander how to do this. And the Alexandrian form has a concept of a title, which I call name, a prologue, a problem statement, some discussions, then the solution, a diagram that may show what the architecture might look like, and then some epilogue. But there are other forms that have been created along the way. Canonical form, there's a couplings form, so the one that he used in his book, of course, the Gang of Four. Cockburn, he created a set of patterns for project management, and he had a form. There's a Portland form, there's a Beck form, Fowler form, and Siemens form. So it seems like most books add their own form, but all of them would have at least these three minimal properties: name, a problem in some context, and a solution. Since the patterns I'm describing are from the Gang of Four book, I should acknowledge the Gang of Four form. And if you buy the book and you use that along with this video, for instance, then it's important that you understand that form. And it will give the pattern a name, and that name is very important. There is a classification in the Gang of Four, so they get classified into a behavioral, or they may be structural, or they may be creational patterns. If there is an alias, then they would also mention something like this. There is a motivation for the pattern. It's specifying where it's applicable. There is a description of the structure. There is a definition of the roles called participants. There is a description of the collaboration that is required for the pattern to work. And then there's a discussion of the consequences of applying the pattern. And then there might be some implementation hints and sample code, and also some known uses of the pattern, places where they know that this pattern has been used. And there may also be a set of related patterns. So they feel like in some cases that one pattern may be related to another pattern or be used together with another pattern. So there is a concept of trying to build a relationship between the patterns in the Gang of Four book. Although I may discuss all the aspects of the Gang of Four form, I'm going to try to stick to a slightly more simple format that I've found to be very useful when I'm presenting this. The default way I'm presenting things is by showing you an example of a problem, then I will try to abstract that problem. Then I'm going to solve the example with a very concrete solution to the example, and then abstract the solution, and that makes up a pattern. There are some cases in the course, particularly when it comes to creational patterns, I may create the pattern language or put the patterns together. And I also do that in the pseudo delegation patterns. It's a category that I invented, but there are a set of patterns that I find very related. Let's take a look at an example of what that means. So the first thing I mentioned was a concrete example. Let's say, for instance, that I want to talk about the shopping list. I went to Home Depot. When I got home, I realized I'd forgotten to buy some nails. Okay, so that's the concrete example. And then I will abstract that and say something like, well, sometimes when I go shopping, I forget things. And then I will go to a concrete solution. Oh, for instance, when I went to the Home Depot, I could have written a list like this, that I needed a hammer and a nail. And as I picked up the hammer, I could have put a little check mark, and I would immediately seen that I didn't have nails. Okay, so that's a solution to the concrete example. And then in the abstract solution, I would basically say, when shopping, you may sometimes forget things. When shopping is the context, my forgetfulness would be the problem. If you write a list that follows some particular structure, this will be a good solution. When you read the Gang of Four, they tend to focus very much on the abstract problem, the abstract solution. And then, of course, we need a name. So in this case, I could name this pattern the shopping list pattern. That would be a full description of the pattern. Anyway, that's the form that I'm going to use most of this course. We strive for a couple of properties for design patterns. One is to find the correct abstraction level. So we try to make sure that it's language independent. The other thing we're trying to do is to make sure that it's domain independent. So language independent means it wouldn't make much sense if a pattern only worked in one language. So we're trying to abstract away from that so it would be applicable to any object-oriented language. It would not be okay, for instance, if we had something like, this is a pattern of how to implement an insurance policy within an insurance company. It may be a pattern, We could create a pattern language around insurance, for instance, but it's not a design pattern at the level of the patterns that I'm going to try to teach you in this course. The abstraction level is interesting because there has been a set of books that by themselves are very interesting, in which we cover patterns in various domains. So, for instance, there is a great book by Martin Fowler on analysis pattern. There is also a book on architectural pattern. There are things on design patterns, which is where my focus is right now, but there are also language specific patterns or idioms, as I'm going to call them. So analysis patterns could be something that says, okay, while you're analyzing a domain or you're writing a specification, these are some common patterns in, say, data structure or how you abstract this, or maybe in business process and so on. Architectural patterns are more structures that often incorporates a set of design patterns. So these could be things like the model view controller, the model view presenter, communication layers, for instance. We have the design patterns that we're covering here, and we have language-specific patterns where someone has written up how to do something, say, in JavaScript or in C++. Now, there are a set of brilliant books that have been written around certain topics. So, for instance, we have Enterprise Integration Pattern, an excellent set of books that talks about how to integrate various enterprise components or systems. We have the JEE patterns, or the J2EE patterns, as they were called when the book came out, called core patterns. And actually, some of the patterns from that structure has penetrated the design patterns world. And for instance, they had something called a data transfer object, first called value object, often called a DTO now for data transfer objects. That has become a very common pattern that probably should have been a very good candidate for the Gang of Four as a pattern. You have books on game programming. There's a book called Game Programming Patterns. There are things on mobile design pattern, SOA patterns, service-oriented architecture patterns. There are patterns on parallel programming, on searches, and so on. This course is going to focus entirely on some generic object-oriented design patterns. Often, an architecture or a framework or a platform is a set of patterns synthesized together. So, for instance, the Java Spring framework uses patterns like proxy, adapter, singleton, facade, template, method. So often these platforms or structure that you see that we're using to build Java applications on are a combination of a set of patterns. And in those frameworks, it's very important to have the patterns vocabulary. So you know when someone says, oh, this is a proxy, that it is different from, say, an adapter or a facade. When you master the patterns, you will find that you're able to communicate with other designers that also know the pattern with a much higher bandwidth. The story that is in this slide is actually a real story from a client that we had in the company I'm with right now, where one of my colleagues was explaining what he had done for a client. The story went something like this. I designed a system for a client X that connected a set of devices in a hospital. I decided to arrange the devices using a composite pattern. I used a remote proxy to talk to the devices, and then to control the devices, I used a command pattern. I combined that with a composite pattern to create complex commands. To get the feedback from the devices, I created a reverse proxy and used the observer pattern to pass events up the chain. The structure ended up being a little complex, so I added a facade for interactions, and I also included a builder for configuration. Now, when my colleague was explaining this to me, I was actually on the speakerphone in a class, and the students were totally perplexed what he was talking about. But I could go up to a whiteboard and draw out the whole class diagram. I have a very good idea of what his design is. So if you master the patterns, you are able to communicate with other people that know the patterns at a very high bandwidth. And being able to communicate the design at this abstraction level is very important. When creating this course, I decided to create all the examples in Java. And that might actually feel a little bit like an oxymoron because design patterns, as I mentioned earlier, should be language independent. However, it's always useful to, in some of the patterns that are very code specific, to show examples in some code. Because I'm using Java, there are certain things that may have been more appropriate to use when I'm showing you the solution. So in Java, for instance, we have a few things that probably was not envisioned by the Gang of Four and certainly not assumed when they were defining the patterns. Things like reflection, for instance, or anonymous inner classes, or maybe even closure, which is coming in Java 8, dependency injection, aspects, if you use AspectJ. There are a set of these constructs that you can implement in Java in a very specific way. I'm going to try to stick to the Gang of Four. Sometimes I'll mention that if you're in Java, you can use one of these techniques. But there has been paper basically focusing on how you could avoid using those patterns if you had some of the more modern language features. I'm aware of a paper that was written on AspectJ where they claim that 15 of the 23 patterns in the Gang of Four book could be implemented more elegantly with AspectJ. But that doesn't diminish the value of the pattern as a way of communicating and as something that you need to understand as a concept. And finally, before you start going through this course, I have some recommendations for you. The first one is don't try to go through the whole pattern catalog at one sitting. I would suggest that you learn one pattern at a time. Think about where you can apply it, try it out, figure out where not to use the pattern, which is equally important as where to use it. And I would also suggest that you try to set up study groups where you have more than one person going through the pattern and where you can discuss it in a group and discuss where to use it. If you can discuss it with your colleagues, the better, because then often you can talk about where those patterns would apply in your current project. Well, with that, I think we've set the context for this class. The next chapters will be all about the design patterns. See you for the next pattern. In this lesson, we'll discuss the composite pattern. I will spend some significant time on this topic as I think it's one of the most important patterns. Certainly, it's one of the most applied patterns. We'll first focus on a few problems where the composite pattern may be applied. Then we will generalize the problem where the composite is a good match. And then I'll take on one of those problems and solve it by applying the composite patterns. And finally, we'll take a look at a few examples in Java and look at some of the specifics on how you implement this pattern in Java. The composite pattern is all about structure, and if we look at an object-oriented solution, we often see objects organized into tree structures or graphs. They may be unidirectional graphs or bidirectional graphs. These have something interesting in them. Often an object in the graph can play two different roles. So this object I'm coloring here might be the parent of these two objects here, but it might also be the child of this other object. Let's take an example from the real world and see how this object structure might fan out. Let's say we wanted to create a structure for an object-oriented file system. Such a system would consist of directories. Let's say this is the root directory. It would have files underneath it, and the root directory may, of course, have another directory, say the etc directory. And the etc directory could have new files or other files and other directories, of course. Although I'm drawing these objects as symbols that we would see maybe in file browser, notice that we have very similar structure. Notice the etc, which acts as a parent of these objects, but is also child of the root directory. So we see a familiar tree structure. If I move this over, I'll show you some of the problems that designers run into. It's not really a problem, but a suboptimal structure. So very often what designers do is they recognize the abstraction of a directory and also the abstraction of a file. So they would come up with some structure very similar to this. They have a file class and a directory class. And then they would recognize that the associations also, all the links that are required. So they may use a composite here, say a directory contains a set of files. But they also recognize that directory can contain a set of directories. And what they're missing is the commonality between the directory and file. At a minimum, they have that in common that they can belong to a directory or they can be contained within the directory. Let's create one more example. In this example, let's take a project management system where we keep track of our tasks and our projects. We will decide that projects has a set of tasks and that tasks are contained within a project. Simple structure with the composite. However, after we used this for a while, users realized that they would like to see a collection of projects also. They want to be able to put together a set of projects and say they belong to a bigger structure. And we might come up with another abstraction, say a super project. And a super project will then contain a set of projects. And perhaps in a little later, people say, oh, tasks are too big of an abstraction. We need some finer grained things here too. So we're going to come up with some elements of tasks. I'm just going to call them elements here. Although such a design will work, it is somewhat suboptimal. The grouping seems arbitrary. Maybe we could come up with some construct of a grouping of sub-elements. The task, the project, the super projects are all very similar. They're a grouping of smaller atoms. Also, one can question whether we need all these groupings. Some projects might benefit from having super projects. Some project may not want the elements, and the depth of the structure seem arbitrary. So if we generalize the implementation problems that we saw, we see that we have similar objects that are organized into structures such as trees or graphs. The depth of the structure varies and must be flexible. We saw that in the project example. A parent may also be a child, true in both examples, and often the object may vary only by their polymorphic behavior. So if you take the file system example, if I wanted to delete an object that is in the file system, from a client's perspective, it would be the same whether I am operating on a directory or operating on a file. They would look the same to me. I'm deleting some element. Of course, the behavior of it might be very different. The file would polymorphically select a behavior where we wipe the file, where a directory would recursively go through its subdirectories and delete all files in it and its subdirectories. Let's show you a final example. In this example, we have a graphical editor. The graphical editor has a set of atomic constructs like rectangles, perhaps line, triangles, circles, ovals, and so on. One of the things we want to support is the ability to select a set of figures, like you can see on the left, and group them together into a higher construct or a grouping of figures. So perhaps we make up a new figure by composing it of other figures. And we also want to do that recursively. In other words, we want to, if we have created a group, create perhaps another group that consists of atomic figures and other groups and so on. This is actually an excellent example where the composite pattern can help us create a very flexible structure. Here we see a possible solution for the grouping of figures. The document here is operating on figures, and the figure is a hierarchy. And the class hierarchy is in a very predictable way. We see triangles and rectangles and so on are subtypes of figure. But notice that we've also introduced the concept of a group. And a group is declared to be of the type figure, but it has this association to figure. So it has a composite relationship to figures. And because it is a figure, we can recurse. In other words, we can have groups of groups, or groups that contains both atomic figures and groups of other figures. Let's get back to the other example. Let's look at the directory and files, where we were building an object-oriented abstraction around the file system. How can we apply the composite pattern to this problem? The first thing we should notice is the commonality between the two composition associations. Both these associations are depicting what directories can contain. If directories and files would have a common supertype, we could have drawn the line from the directory to that common supertype. It is often difficult to name that common supertype. I'm just going to call it file item in this case. Now that we have introduced this common supertype, we can erase the associations and replace it with a single one. Now that means we have applied the composite pattern. The directory plays a particular role that we're going to call composite. The file item is an interface or some common abstraction between the atomic elements or the leaf elements, here being the file, and the directory being the composite. In the pattern, we're going to see that's called component. Now, I would argue that having a single line representing the containments of directory is a better data structure. And it's going to have a few other advantages, as we'll see later.
particularly one of delegation, but I'll show you examples of those advantages when I do the Java code. Once the common supertype is in place, you often find that the composite structure and the atomic or the leaf components have more things in common. These things could be simple properties like name and size, but it could be complex operations like delete. Of course, delete would require some kind of recursive calls for directories and a different polymorphic behavior than for file, but it could also be complete constructs like the access model, for instance. We applied the composite pattern twice. We did it once for the graphical editor and the figures, and once for the file system. For it to be a pattern, we need to abstract it somewhat and talk about the pattern at a more abstract level. So in our example, we had a composite, and the composite was the directory in the file system, it was the group in the graphical editor. We had the concept of leaves, or atomic components. The leaves were the files in the file system, and they were the rectangles and the ovals and triangles and so on in the graphical editor. We introduced a common abstraction between the composite and the leaf. In the pattern, that is called a component. Then an important thing is we have this composition relationship between the composite and the component. And the interesting thing about that association is that it is recursive. The idea here is that the composite can contain components that are atomic or other composites. And often a client would operate on the component without knowing whether it's a composite or an atomic component, or a composite or a leaf. So in the composite pattern, we have three roles. We have the component, the leaf, and the composite. The component is the common abstraction that we found between the leaf and the composite. That is often implemented as an interface in Java, but it could be a base class also. The main idea here is that the clients can operate on leaves and composites in the same way. In other words, they have some common interface. It also is the target for the composite association, so that the composite can contain components, and leaves and composites are components. We also have the concept of a leaf. A leaf is the atomic elements in the object graph or tree. The composite is obviously the one that holds a set of children. It stores child components typically, although sometimes you'll see that component actually keeps track of what composite it's in, but that's more rare. In Java, we have some specific issues when it comes to implementing the composite pattern. First of all, we have the advantage of garbage collection. And that makes often these graph structures a lot easier to implement than, say, in a language like C++. Another issue we need to wrestle with is the associations and their direction. Most common is that the parents store a reference to its children, perhaps using one of the collection classes. But in some cases, you're actually better off having a child know about its parent or parents. The component role is also often an interface. In many cases, you introduce both an interface and a common base class, because often there is some part of the implementation also that are common between the leaf and the component. I'm going to implement an expression framework. The use case for this is that we have some system where some external user wants to configure an expression. Perhaps because some part of a calculation needs to be configurable. So say, for instance, that a user wants to add a calculation to a system. For instance, we need to add 3 plus a divided by 5. This would typically be in the context of some rule-based system where we're allowed to, as a user, configure up some behavior of the system that is math-based. So what kind of object structure can we create to solve such a problem? I'll minimize the context and put it up in the corner for you. And let's write down an example so we can see it. Let's say we have 3 plus a divided by 16. So what are the objects in such an example? I would argue that pretty much everything that has a symbol is an object here. The plus, the 3, the divide, 16, and a being some kind of variable. When we draw this graph, we will start at the root, which will be the divide, and then on its left side it has a plus, on its right side 16, and the plus has on its left side the number 3, and on its right side the variable a. if we looked for the class that each one of these objects would have to be a member of, we could start with the a, which has to be a variable. The number 3 is an example of a constant. The plus is an example of an operator capable of adding its left side and right side, in this case 3 and a. I'll simply call the class adder. I'll call the root object a divider. Now this is a complete object graph that represents the expression that we want user configurable on the left-hand side. Now we can clearly see the composite structure here. The expression forms a graph. What would this look like in a class diagram? I'll minimize this drawing so we have space for a class diagram. You probably remember from the theory section that we had these 3 classes or types. The component, which is the base class, the composite that contained other components, and then the leaf, which was the atomic component. The question now is, how does that relate to the structure that we saw with the expression? Well, I'm going to replace the name component with expression. When we go ahead and implement this, this will most likely become an interface in Java. The leaf will become an atomic expression, and we've seen 2 examples of such. Constants and variables always formed leaves in the tree structure that we saw. In other words, constants and variables do not have children. The composite, however, is a little more tricky. We actually saw several composites, the divider, the adder, and we probably have a subtractor and a multiplier also. I'm going to create a common base class for these, and I'm going to call them binary expressions. The binary expressions have a very special implementation of the composite association between the composite and component. They have a left side and a right side. It's not an arbitrary number of children. They always have one left child and one right child. So we need to replace the association. And we see a couple of examples of the left association in the picture on the left. And we also see a couple of examples of the right association. I assume the binary expression will become an abstract base class, so we also need to add the concrete subclasses of the binary expression. We would need something like the adder, probably a subtractor, the divider, and so on. As you can see, the class diagram looks quite different than what we had perhaps expected. It looks different from the composite. But the composite structure is still there. You can clearly see how we're building up a recursive structure using the binary expression. Now for something a little more exciting, let's move the class diagram to the side so we can get some space again. I'll redraw a similar structure to the one we drew before, with a divisor on top. On its left side it has a plus with 3 and then say a variable a, and then on its right side a constant 5. And let's take a look at how we would calculate the value of the expression at runtime. Now the trick here would be to ask the root object what its value is. Of course, a divisor cannot determine that value without first figuring out its left side. So the divisor asks the plus what its value is. Now importantly, the divisor doesn't necessarily know what's on its left side. It just knows that it can ask for its value since it is an expression. The plus will ask its left side and get the value 3. The plus then asks its right side and get the value of a. And now it can return the value to the divisor. And the divisor now can resolve its right side by going to the constant 5. Now let's say for instance that the value of a is 10. Then we will get 3 from the constant and 10 from a. We need to add those together. We're going to return 13. The divisor now resolves its right side, get 5, and returns the result being 13 divided by 5. Now this kind of recursive call through the object structure or delegation through the object structure makes the composite an extremely powerful pattern, one that we use very frequently and one that you'll see be very powerful as we apply it in different situations. I'm going to take a test-driven approach to building the example of a composite. I'm going to start by creating a JUnit test, and I'm going to call composite test and put it under com/spike.composite.test. I build this simplest test first, one that tests the constant. And I'm going to write code like if I had already implemented it. I'm going to create an expression that I call E that takes a new constant, and I need a test value, which I'm going to set to 3.0. And then I'll write an assert statement to make sure that it works.
that compares the test value to the value returned from the constant with a fault tolerance of 0.0. But of course, I don't have this implementation, but Eclipse can help me here. And the tip that is on the left-hand side on the bar, I can use that to create an interface that is the expression that I'm missing in the test. Eclipse will initiate the wizard with the correct values, except I don't want it in the package test, so I'm going to go up one package. Now that we have the expression interface, we can go back to the test class and fix some of the other errors. I'll first add the getValue method to the expression and change the return type to double. As I go back to the unit test, I see that I also need to create the class constant. Just fix the package declaration and we should be good to go. So that created a class. Now let's go back to the unit test and see what else we need. We need the constructor that takes the value. Test value is not a good name here, so I'm going to use value. And then I'm going to use a little trick in Eclipse, just say this value equals value, and then let Eclipse create the field for me. Finally, we need to fix the getValue method and make sure we return the value passed in the constructor. And now we can get rid of the final error in the test class. We need to basically statically import assert, so I can write just simply assert and not assert equals. It's just a little shortcut. Then let's finally run the unit test and make sure that it works. And yes, we get all green and everything looks good. So we now have a constant. So let's go on to a more complex implementation. Let's create the adder. Here we should be able to create a couple of test values. Let's say 2.0, 4.0, and then we should be able to create the expression. However, the adder should take expressions as parameters. So we need to wrap these test values into a couple of constants, call them left and right. So they add up to left and right. And then all we need to do is to write the assert statement. The assert statement should compare the test value A plus test value B and the value from the object under test, E in this case, so E.getValue. And the tolerance we should be able to do simply 0.0. Again, I took the approach where I wrote the unit test before I had implemented the adder, so of course we have an error on the line where we create the adder. I'll use Eclipse again to create the adder class and put it one below the test package, so in comp size by composite. Now the adder class needs a constructor that takes two expressions, the left and the right. And I can use the trick again by saying this.left equals left and this.right equals right. And then use Eclipse to construct the two fields. That's just, again, a shortcut. And finally, we need to fix the getValue method. And all that should do is to go and grab the left value and then add that to the value from the right-hand side and return it. So we can now try to save the file and run the unit test again and see if it all works. And it looks good. Everything is green. Our tests are passing. Now let's create this test for the subtractor, and I can simply copy the adder and fix it. So I'm going to rename it to test subtractor. Instead of creating an adder, I'll create the subtractor. And then of course I need to test it against a subtraction of test value A and test value B. This time it makes more sense to copy the adder to create the subtractor instead of using the quick fix. And I can do that by simply dragging the adder onto the package. That will make a copy. I'll rename it and I'm going to call that class subtractor. I'll open up the subtractor file. And really all I need to do to this is to change the sign. So change the plus to a minus and we should be done. In the test class, I will have to import the subtractor and then we should be able to run it. When we run the unit test again, we see that we now have 3 tests and they all succeeded, all green. So what we did with the adder and the subtractors, we did a copy and paste. Whenever I do that in Java, I feel like I'm missing some common abstraction. So I'm going to introduce a common abstraction for all the binary expression, adder, subtractors, divider, and a multiplier also. I'm going to select the expression and then create a class that I'm going to call binary expression and that implements the expression interface. This new class binary expression, we need a constructor to take the left side and the right side. And I'll use the same trick as we used before. by writing this dot left equals left and this dot right equals right. And I also need to remove this implementation because we don't know how to get the value at this level of abstraction. We'll add the two fields and make sure that the class is declared as abstract since it doesn't implement the getValue method. I'm just going to make it simple here and make these fields protected. Now that we created this common abstraction for complex expressions, we can now refactor the adder and the subtractor. I'll start with the adder and I'll make it extend binary expression instead. We don't want to have the fields ourselves since they're on the base class, so I'll change the constructor to simply call the superclass constructor. And then we can remove the left and right side. And that should do it for the adder. Then we'll make the equivalent changes to the subtractor also. Well, we made the adder and the subtractor a little bit simpler by introducing binary expression. I'll launch the test and make sure it all works. And it looks like it does. Everything is green and we're good to go. It should be very easy for us now to create the divider and the multiplier. All we need to do is to simply drag the adder and create the divider. And the divider, we need to change the sign to use divider instead of the plus. And we can do the same thing with the multiplier. Just open it up and then change the sign here to a multiplication. And we should now have the 4 basic operators. Let's finish up some tests also so we have tests for all the operators. We should be able to copy the existing test for subtractor. Just make it for the divider first and make sure we divide. And then we should make another one for the multiplier and of course replace the operator with a multiplier. And then we can try to run it and take a look. Oops, I did not attach a test tag. So we'll have to do that. Put the two tests together and I see I have an error again. Let's see what I did now. Okay, so I forgot to change the subtractor out to create new dividers and multipliers instead of keeping the subtractor. So we'll do those changes too. We'll see if it works. And with that, I think we completed up the framework. So let's take a quick look at what we're doing in drawings. Let's assume we have a fairly complex expression, something like this. 3 plus 5 multiplied by 100 divided by 2 plus 64, for instance. Now, what exactly would that look like as an instantiated object graph? Using our implementation, this expression will form a tree structure where the root object will be the divider. This is simply because the divider is the expression that has to be executed last after whatever is above the divider and below the divider has been calculated. On the left side of the divider, we have a multiplier. The multiplier has on its left side a plus or an adder. The plus has on its left side a 3 or the constant 3, and then on its right side the constant 5. Going back up to the multiplier, it has on its right side the number 100 or the constant 100. The root divider has on its right side a plus, and that plus or adder has on its left side a 2, and then on its right side the number 64. So using the class structure that we have now, we should be able to instantiate this object graph. And what's interesting after that is exactly how do we evaluate this expression, or how do we calculate? And this is one of the big powers of the composite structure in object-oriented software, because every object can have a method, and we can actually use delegation through the tree structure to execute the behavior that we want. So for example, if we were to ask plus what its value is, it wouldn't know by itself, but it could delegate to its left side where it finds 3, and then from its right side where it finds 5, and then say my value is 8. The multiply would take its left side, which is the plus, and find that its value is 8 times its right side, which is 100, and get to the value 800. The right-hand side of the divider's plus will find its value to be 66. Finally, we get to the divide, which by delegating to the multiply found 800, delegate to the plus, got 66, and will then divide 800 by 66. 66 go into 800 12 times. 12 times 66 is 792. That leaves us 8.
So we should get something like 12 and 8 over 66, which is 12 over 4 over 33. So that would be 12.4 over 33. That would be 0.12121212. Try this out in code. Let's create the test case for that. I'll just call the test case for test complex expression, and then we'll construct an expression E. The example I drew had at the root a divider, and the divider had on its left side a multiplier. That multiplier had on its left side a adder with two constants. One was 3.0 and the right side was a constant 5.0. The multiplier had on its right side a constant which we said was 100. That completes the multiplier, so we just have to finish up the right side of the divider, which was an adder, which added two constant, 2.0 and 64.0. Let's see, we just get the parentheses right here. I think that completes the expression actually. So now all we need is an assert. Now we calculated while we were doing the drawing that the result of this expression should be 12.1212121212 and so on. So we need to write an assert that checks that. So we'll create assert equals 12.12121212. Don't need to fill it all out. And then we compare that to the expression's value. And I'll just put a reasonable fault tolerance here. Then all we need to do is to run the unit test and see if we get the right values, and we did. So we now have implemented a fairly complex example of a composite, the example being this expression framework. I've showed you the composite pattern. It is one of the most applied patterns. In fact, when I interview object-oriented designers that applied for work with my company, I always give them problems to solve where the composite pattern can be used. That is a showstopper for me if a candidate does not know the composite pattern. The composite pattern is a way of organizing objects into structure. The most common structure is a tree, but we occasionally also use the pattern to build more complex structures in general. The pattern is easily recognized when viewing a design in a class diagram. You will see the characteristic loop that spans inheritance, but also associations. The inheritance is used to capture the commonality between the leaf and the composite. We often organize, or we call that root concept and component in the pattern. The association is there to allow for the organization of objects. With that, we conclude this session on composite. We'll see you for the next pattern. In this lesson, we'll discuss the proxy pattern. The proxy pattern is very common in object-oriented implementations. If you have been programming in Java for a while, you'll probably been using it. However, you may not know that you've been using it, as it is often implemented behind the scene in libraries that you may use. It is a very important pattern in libraries such as the JEE and the Spring framework. Even though it's a very common pattern and most developers seem to know it, I've noticed that the pattern is often misunderstood and confused with other patterns, particularly patterns such as Facade and the adapter, mediator, and the decorator. In this lesson, we'll take the familiar approach of looking at a few problems where the proxy pattern may be applied, generalize that problem, apply the proxy pattern to one of these problems, generalize the problem to form a pattern, and then look at how the proxy pattern can be implemented in Java. Let's take a look at the problem that we're trying to solve. Let's say we have some client, and that this client wants to access some object. Turns out that this is not possible. There could be many reasons for this. Perhaps the object is not directly available. The object may, for instance, live on another machine, or it may have been swapped out to a disk, similar to what we see, for instance, in JPA or the Java Persistence API. In other examples, there might be some processing that is required. This processing should not be done by the object itself or not by the client. Some examples of those could be security.
we need to make sure that the client has the proper credentials to access the object. However, we don't want the object to be aware of the security, nor do we want the client to have to implement the security. There might be other reasons. For instance, we could have a requirement that audit trails have to be produced in some form. And we don't want the audit trail to be the responsibility of the client, in this case, not even by the object. There could be many, many other reasons why we can't connect the client directly with the object. Perhaps we want to make sure that we're doing some timing whenever it's accessed, and we don't want the client to have to deal with this, nor do we want the object that implements the business logic to have to deal with this. When you encounter these problems, that's when introducing a proxy can be appropriate. A proxy is an object that represents the real object, and where the client can use the proxy to communicate with the real object. In most cases, we would want the proxy to look and feel identical to the real object. The proxy implements the same methods as the real object. It may, of course, be somewhat of a delay involved here, as we'll see in some cases, but the algorithm inside the proxy typically contains some processing, maybe some pre-processing and post-processing, but one of the things that it would always do is to forward the request to the real object. Very important that the client does not see or is involved with the actual proxy handling. It looks to them that they talk to the real object. Let's take a look at a few examples, and I'll remove some of the text from this slide. In this first example, let's assume the reason the client can't talk directly to the object is that they live in two physical addressing spaces. The object may, for instance, reside on the machine in New York, and the client may live in San Francisco. A common way to solve this is to introduce a proxy on the client side, that is within the client's addressing space, that knows how to find and to communicate with the real object in New York. In most cases, it turns out that this pattern can be automated, typically through code generation from some interface library. You may already have been using this pattern, but you probably use some kind of library that was provided for you. This library would typically generate the proxy, or there is something called dynamic proxy that might help you with this also. What's important, if the library was good, it should have ensured that the object looked local to you, the client. Some of the libraries that you may have used could be something like Corbal, that is getting to be pretty old these days, or Java RMI. There are tons of other libraries out there. All of them typically have some concept of an interface that you define, and then they would generate a client-side proxy. In many of these libraries, there is actually also a server-side proxy, but you typically don't see that. Let's use another example. In this example, the client and the object is running in the same machine. The problem here is one of security. In this implementation, we must ensure that the system checks the credential of the client and that the client has been granted access to the object. However, we don't want the business implementation of the object to be involved in security. If we did, then the security code would be spread all over all the business logic. Nor do we want the clients to check themselves. Perhaps we don't trust them, or we don't want the security code to be spread out among the clients either. What we can do is to introduce a proxy that sits between the client and the business logic. The proxy would implement an algorithm where they first check to see if the client has permission to invoke the business logic. This could, of course, be using some fancy security library. And only if the client has such permission would we forward the request to the real object. If the client does not have permission, we could, for instance, throw an exception or take another evasive action. Notice in these two examples that I created for you, I was able to use basically the same drawing. All I did was provide some context. This is clearly showing that this is a pattern. And of course, I could have created all kinds of other examples. This processing could have been for logging, for instance, to create an audit trail, timing if we're checking performance. It could be something that restored the object or retrieved it from disk and then instantiated it in memory. There are so many different examples where the proxy pattern is a good choice of implementation. Another interesting thing about the proxy pattern is that we often chain proxies. In the examples I've shown,
I had a single proxy sitting between the client and the business object. But we could really imagine a set of proxies where one proxy is forwarding to another proxy, that's forwarding to a third proxy, allowing us to dynamically add behavior in a connection between a client and a server. Let's look at this pattern in a more formal way. What does the proxy pattern look like in a class diagram? Let's start with the client. The client is accessing some object of some type. I'll just call the type component. The client shouldn't necessarily know if they're operating on the real object or the proxy to the real object. The client should really work on an interface. The real business object then have to implement this interface to ensure that they fulfill the contract, and the business object holds the actual business algorithm that we eventually have to have invoked on behalf of the client. A typical way of ensuring this is to define a component as an interface and have the business object implement this interface. In RMI, there is a slight discrepancy here. So think of the diagram that I'm drawing as more of a conceptual diagram. We also need to implement a proxy. Now, the proxy would have to have the same methods as the component interface, and typically all it does is to forward to the real implementation or to another component that may be a proxy or a real implementation. Think of the proxy as a subtype of a component or as a class that implements the component interface. Also, the proxy will have to have a reference to the object that it needs to forward to. So this makes up sort of a conceptual diagram of what a proxy does. A proxy is something that implements the abstraction that the client is expecting. Its goal is to forward the request to the real implementation, but perhaps it's doing some pre-processing and post-processing before or after it sends the message onto the real object. Now let's look at an example of the proxy pattern in code. I'll make the example as simple as possible. So say we have a business object, and I've created a simple class that I call Business Object Implementation. The business object implementation has a single method called sayHi, and all the method does is print out the message. I've also created another class that I use to test the business application. I've called this class main, and the main method in the class main simply creates an instance of the business object implementation and calls the method sayHi. If I now run the main class, we get the expected behavior. The business object implementation prints out its message. Now let's see if we can create a proxy for the business object implementation. The first thing I'll do is to introduce an interface to the business object. And the best way to do so in Eclipse is to use the refactoring tool and simply specify that I want to extract the interface. I'll specify that I want to include the method sayHi, and I'll call the interface business object. Eclipse will now introduce the new interface and make sure that the business object implementation extends the business object interface. Eclipse has also refactored the main class and sees now that the only dependency within the main function is that we are using the interface. So instead of having OPG declared as a business object implementation, changed it to just be the interface. And if we open up the interface that we just created, we see that it only has this one function called sayHi. Next, let's create the proxy. And I'll select the interface, right-click and say New Class. This makes sure that Eclipse understands that I want to create a class that implements that interface. I'll call this class Business Object Proxy. And we notice that the newly created class implements the business object interface, and it has a method that we override called sayHi. The first thing I'll do is to create a constructor for the class that takes a business object that I'm going to call the target. Target will be the object that I'm going to forward the requests to. So I need to store that target somewhere. Assuming I have a variable called target, I could say this.target equals target. Eclipse will show an error because I don't have that variable, but I can now use the quick fix to introduce that variable. I'm going to, of course, use that variable in the sayHi implementation, where all I want to do is to forward the request of saying hi to the target object. So this is the simplest form of a proxy. Of course, it's not very realistic. It's not adding any value at this point, but at least we have the forwarding behavior that a proxy is supposed to have. Next, let's go over to main and make sure that the main uses the proxy rather than the business object implementation directly. Let's simply wrap the creation of the new business object into the creation of the new business object proxy, so that we pass the new business object implementation to the business object proxy. Now, if we run the main again, we should see exactly the same output, because we're basically just forwarding the request to the business object implementation from within the business object proxy. So now the main is using the proxy, and the proxy forwards to the main implementation. So let's run main, and we see that indeed we get the same message. Hello, have a nice day. Of course, the proxy wouldn't be worth much if all it did was to forward the message. So let's add some behavior to the proxy. I'll open up the say hi method, and then I'll just simply add a print statement before and after the say hi. Now, of course, this should be more complicated. Maybe what we did is restore it from a database or doing something else. But the point here is that we were able to introduce some behavior into the application without changing the client or changing the actual business object. And this is the value of a proxy. So let's try to run it and see what happens. We get the about to call the real, then we get the forwarding that results in the business behavior, and then we get the conclusion. So we get pre-processing, the real implementation, and some post-processing. We're not touching the client, we're not touching the business object, and we're still able to introduce some processing. And this is used all over in Java frameworks. Like Spring, for instance, uses this heavily. But we have some things that we really should clean up. The way it works right now is that the proxy is known to the client. The client that created the business object implementation also had to create the proxy. Now, typically this is done with some kind of factory. Now, we haven't discussed the creational patterns yet, but I'll make a simple example of how we could have hidden this from the client. What I'm going to do actually has a name in the patterns world. It's called the factory method. But for now, I'm just going to make it very simple and just explain what I'm doing. I'm going to open up the business object interface. Now, if we were working in Java 8, I could have actually not made the change that I'm about to do, because in Java 8, I'm allowed to have functions within an interface. But since most of you probably will be on 7, I'm going to actually change the business object from being an interface to being an abstract class. The reason for this is that I want a static method on the business object. For this to work, I have to make sure that the business object proxy and the business object implementation extends instead of implements the business object. Now I can get back into the business object abstract class and add the method, I'm just going to call it create, that returns a business object, and that hides the complexity of creating a business object implementation and wrapping it into a proxy. Now let's go back into main and hide the complexity of the proxy from the main class, who is our only client in this case. So instead of all this complexity, all we need to do now is to call the static method on the business object create. And if we run this, we'll get exactly the same result. Notice how much easier it is on the client. All the client does is it says business object.create. It gets back something. It doesn't know if it gets the real object or the proxy that then forwards to a proxy and then to a proxy and then to the real object. All of that is hidden in the create method. Some of the most difficult thing about the proxy pattern is to figure out a good way of introducing the proxy in between the client and the server. So let's wrap up the proxy pattern. The general problems and forces here is that the client wants to use an object that for whatever reason cannot be directly accessed. Typically this is because some code must be run that is not the concern of the client nor the implementer of the object or the service itself. This could be things like security. Often we don't want the business object implementers to know anything about security. We want them to just run without having to worry about it. We don't want the client to enforce security either. So we need someone to implement security in between the client and the server itself. It could be remote communication, it could be the setup of transactional context, it could be logging, it could be any of the other things that you can imagine that is not the concern of the client nor the concern of the implementer of the objects. Our solution is to have the real subject implement an interface that I've called subject and have a proxy, here illustrated with a remote proxy, that implements that same interface. The client will work on the interface and not necessarily know whether they're working on any proxy or the real subject. The proxy's responsibility is to overcome whatever hurdle, security, remote communication, whatever it is, and then forward the request to the real subject after it has performed whatever service it's performing. In Java, we typically implement the top-level interface as an interface construct as opposed to an abstract class, for instance. And there are some other implementing options that you have in Java that is outside the scope of this course. You could use a dynamic proxy, you could use AspectJ, all very powerful for introducing proxies in between the client and the real object. In this session, we'll take a look at the adapter pattern. The adapter pattern is very often confused with the proxy pattern, so we'll also contrast them. It's also confused with things like Facade and Decorator, so as we go through all the pattern, I will come back and compare them. We're first going to look at a few problems where the adapter pattern may be applied, generalize that problem, and apply the adapter pattern to one of the problems. I'll generalize the problem to form a pattern, and we'll look at the adapter pattern and some implementation tricks for Java. Let me illustrate a very common scenario where I've used adapter pattern in many different projects. Let's say we have some business object. Let's say this business object supports a single method named f. Let's also assume we have a set of clients that depend on this business object. Somewhere in their implementation, the clients will call the business object's method f. Now let's also assume that we find a much better implementation of the business logic. We may, for instance, find an open source project that implements exactly what we want, but much better. However, it turns out that although the better open source implementation implements exactly the same functionality, they have a different interface. The name of their function is G. Now we have a dilemma. If we introduce this new and better implementation, all our clients will have to change. The change may be trivial, but often it is risky and inconvenient, particularly if the clients are external organizations. This will, of course, be not good for our reputation and leads to very unhappy clients. The adapter pattern suggests a solution for this problem. The idea here is to introduce an intermediary object that translates from what the clients want to see into what the implementation requires. In our simplistic example, we would simply introduce an object that the client used that supports the method f. In the implementation of f, we simply call the better business object implementation's G method. Notice how we no longer require changes to the client's code. And over time, we can now remove the older business object without affecting the clients. Let's study this pattern in a UML class diagram. In our example, we had an old business object implementation that supported the method f. We found a better business object implementation that had the method g that was semantically equivalent to the old function f. For this to work, we need an interface that abstracts the old implementation. Normally that would be there in a good implementation, but if it wasn't there, we would have to introduce one. Now we need to introduce a new implementation of the business object implementation, or at least the interface, that we're going to call the adapter. The implementation of the f method in the adapter is quite trivial. It would have to forward to the new business object implementation and translate from f to g. To be able to forward to the new business object implementation, adapter would have to have a reference to the new business object implementation. Now, assuming that you already went through the pattern for proxy, this may at first look very similar to the proxy pattern. But notice here, the adapter is not forwarding to an object with the same interface, it's translating it from one form to the other. That makes it different from the proxy pattern. To show the adapter pattern in Java, let's take a simple example. So in this case, I have a logger that I've implemented, and here's some client code, and all it does is to create the logger using this method on an abstract class that we've seen before, and then we debug and trace and log. There are different methods on the logger that allows me to produce log messages. If I open up the logger, you'll see that I've implemented that as an abstract class. I wanted to have that static create method. And you see all it does is return a logger implementation. But at the same time, of course, it also plays the role of an interface. The logger implementation is a very simple class. All it does is print to the console the log messages. Now, any Java programmer would know that there are a set of log libraries out there, and I should have used one of those. And I'm just going to simply integrate the Apache's common logging and have that work over log4j. I've set this project up to be a Maven project. Maven has this advantage that I can go and grab code or grab libraries from the open source. So I'm going to open up the POM file and just specify that I need to use the Apache common logger, version 1.1.3, which is the latest one at the time I'm recording this. And as soon as I save the POM file, Eclipse will download and add the library to my project. I won't show you that. I'll make exactly the same exercise for log4j. The interesting thing here is that the common logging framework or commons logging framework from Apache has a different interface from the one that I had originally specified and that was used among maybe thousands of clients in my project. What I need now is to introduce commons logging and try to do so without the clients having to change code. So what I'll do is I'll create a class that implements the logger interface, and I'm going to call it Apache Commons Log Adapter. Eclipse will now create a class that has a dummy implementation of all of the methods that I need to implement. The Apache Commons have this log just called a variable logger, and I'm going to instantiate an implementation of that. I'm going to use the log4j. And next, I'll implement each one of these methods by forwarding to the logger and translate where I need to. For trace and debug, the translation is straightforward, but for log, there is no such method. So I'm going to use info instead. So here we have an excellent example of an adapter where the log message is translated into an info, but semantically, they're the same. That is, the info that we use on the commons logger is meant in the same way as the log message was originally meant for my own implementation. Now I'll go back to the abstract class logger and change the create method to use this adapter. And the interesting thing about this is by having created that factory method and separating the interface from the implementation, I'm able to introduce this new Apache Commons library without changing any of my clients. Let's summarize the adapter pattern. The general problems and forces is that we sometimes have business applications not usable or reusable simply because of a mismatch of interface. Semantically, whatever the business application is doing is correct. However, we have clients that depend on a particular interface. To solve this, we implement a version of that interface called an adapter that translates the methods that the client wants to see into what the business application called the adaptee wants to see. In this session, we'll take a look at the decorator pattern. The decorator pattern is often confused with both the adapter, sometimes even with composite, but probably most common, the proxy pattern. As usual, we'll take the same approach as we've taken in all the other lessons. We'll take a look at least one problem where the decorator pattern can be applied. We'll generalize that problem. We'll apply the decorator pattern to one of the problems, and then we'll generalize what we have done to form a pattern. And then finally, we'll look at how the decorator pattern can be implemented in Java, or look at one example where the decorator pattern has actually been implemented and is part of the library of Java. Let's assume we want to create the user interface library. We'll allow the programmers to create a set of widgets or UI objects. For our example, let's focus on one of these widgets, namely the text box. The text box allows the user to enter some text over multiple lines.
In some cases, we allow the user to type on after they filled the text box. If we do, we should probably have a variant of the text box that allows for scroll bars. These scroll bars would allow the user obviously to scroll up and down and see the text that is outside the window designated. Let's say we want to create a class that can do that, and perhaps we create a special kind of class for the widget. Maybe we will call this something like text box with scroll bar. Someone else want to also have something like a border or a double border around. Perhaps we create this class something like text box with scroll bar and double border. And you see the problem here is that we have scroll bars and borders, and these are independent dimensions. If you want independent features, we might, for instance, also introduce shading. The number of subclasses of the text box would just explode exponentially with the number of factors that we come up with. If we went back to the 80s and even the 90s, designers often tried to fit all these variations into hierarchies of classes. We may, for instance, have a base class called widgets, and then we have a subclass called text box, and then we get all these variations of text boxes underneath. Modern designers usually do better than this, and we hardly ever see these design constructs anymore. Remember that the design patterns book was written back in 1994. And at that point, using class hierarchies to solve these type of problems were very common. The decorator pattern is a great way to solve this problem without introducing a combinatorial number of specific classes. One of the beauties of the decorator pattern is also that the features can be added dynamically at runtime. Let's first think about this conceptually. If we have a client with a text box, what he wants is for the scroll bar and double border to be added rather than to think of it as a completely new type. In fact, we want to dynamically introduce perhaps a scroll bar at the point when the user has typed too much text, or we might want to introduce the double border to show selection of a text box. So it's more of a combinatorial thing. It is also worth noting that these things that we add to the text box could be potentially reusable. We could, for instance, use the scroll bar somewhere else. There wouldn't be much difference for a scroll bar for a text box versus, say, a scrollable picture for pictures that are too big to fit into a frame. We also want for these features to be runtime extendable, so that a user or the text box could add these features whenever they feel it's essential to have them. Let me create a new picture where I'll show you the decorator pattern applied to the text box. Let's say we have a client that at runtime creates a text box. The client can now start adding content to the text box. I'll draw what that might look like on the right-hand side. Let's say we have a box that contains the text, and as we're adding content, we'll keep on displaying that content inside the rectangle. However, at some point, we might go beyond the designated area for the text box. And as soon as we do, we need to add a scroll bar. We want the scroll bar to be added, but we don't want to change the type of the text box. The decorator pattern suggests a way of doing this. Now let's assume that the client is using some object, so we can just draw the text box object and the reference from the client to the text box. What the decorator pattern suggests is that we introduce a new object that sits between the client and the text box that is responsible for rendering the scroll bar. Now don't worry too much right now of how that gets injected. I'll give you a couple of alternatives for that later. But just notice that now whenever the client is using the text box, they actually go through the scroll bar before they get to the text box. This is an interesting way of doing things because the scroll bar gets to, for instance, render its area on the screen and then maybe narrows down the size that is now available for the text box to render. In our example with the scroll bar, it would be natural that the text box itself injects the scroll bar. Let's look at a different example where it might be equally natural that the extended functionality is added by a client. If we wanted to add a border to the text box, it would be natural that the client requests this. The mechanism would be the same though. What we would do is we create a border renderer in front of the scroll bar renderer in front of the text box. This way we can chain together different features for a widget. In this case, we're using the text box, but you can probably see that we could have done exactly the same for a picture. We call these extensions for decorators. They were introduced dynamically and they're potentially reusable. Looking at the general problem and the forces, the key to the decorator pattern is that we want to extend objects' behavior at runtime. This is often done through inheritance, but it's not practical as we would need to know the concrete behavior a priori. We also may want to revoke the functionality at runtime. So it's a lot about dynamically being able to configure behavior of some component. In the example that I drew, we looked at a text box and how we might introduce a scroll bar when the text overflows the area on the screen. We also looked at maybe introducing a border decorator or some kind of border that was added dynamically whenever a client asked for it. The design pattern for the decorator suggests a very concrete solution to this. In this example, I used a base class or an interface called graphical component. We see that we have a subclass called text field, but I've also introduced a decorator. And this would be an abstract class that holds the behavior that forwards to another graphical component whenever it's painted. So notice this chain that we've created where the decorator has a link to the graphical component. Therefore, some people think, oh, it's like a composite. But remember, the composite was just about structure. This is about behavior. What we want to do is to be able to dynamically link new behavior or add new behavior to any graphical component. The generic decorators that we've created, scroll bar decorator and border decorator, each one of those, by virtue of being a subclass of a decorator, would have the paint behavior where they do their work and then just forwards to the superclass to delegate to the next component in the chain. So we have a general solution. We have some component. There are various concrete components that we can decorate or add functionality to that on some method, it was paint in the example of the text box, but here generically some method. We want to decorate. We create a decorator that implements a very particular behavior. So there's an abstract decorator that really just forwards to the component. Then we have various concrete decorators that implement some specific behavior. And you see in the method of the concrete decorator, we are perhaps doing our own special method and then forward to the component. Or maybe we decide that we need to do something before we forward to the next component and after we have forwarded to the next component. This allows us to add behavior. Now it's important here that the decorator extends the base class, because a client may not be aware of the fact that they're using a decorator. So all they see is the method on the component. Now it could be that the real component they think they're using has been decorated, and therefore they're going through a chain of behavior before they actually reach the component that they think of. There are a set of real specific design considerations that we have to take into account when using the decorator. First of all, the decorator itself must conform to the component's interface. This is important so that we can shield the clients from the complexity of the decorator. If the component hierarchy is responsible for the injection of the decorators, then it might be a good idea to ensure that the component interface on all mutating operations return a component. This is often called a fluid interface. I'll show you some examples of that when we get to Java. May also want to use factories to help create the initial configuration of components. This is useful if you use decorators in a static context, where you're not actually dynamically adding behavior at runtime, but it's just a convenient way of implementing a set of orthogonal or independent concerns. A couple of techniques that may dramatically improve the usability of a decorator solution is the use of dynamic proxies and also aspect J. The use of these two constructs is outside the scope of this design patterns course,
But you might want to look at how to use dynamic proxies for implementation of decorators, or maybe Aspect J.
Let's take a look at an example from the Java libraries where they use the decorator pattern. An excellent example of the power of the decorator pattern can be found in the Java I/O library. Here I have a simple algorithm where I create a file output stream, write some content to it, and then finally close the stream. Notice that the stream is being used in two places: in the main method where I construct and close the stream, and also in the function that I called write some content to the output stream. I can execute this class, and then if I refresh the Eclipse directory, I'll see this new file called test.txt. What is interesting now is that I can introduce new behavior at runtime without affecting either the main method or the other function that creates the content. Either one of them can introduce decorators that change some of the behavior of the example. Let's illustrate that by adding a gzip output stream to decorate the file output stream. I'll have to change the name of the file to test.zip, and then I'll wrap the existing file output stream into a gzip output stream, which is really the decorator in this example. Now execute again and refresh the Eclipse workspace. You will see that we have this test.zip file. And notice we did not have to make any changes to the write some content to an output stream function to do this. We could also introduce a decorator at the function level here, or inside the write some content to output stream function. I could, for instance, introduce a buffering in this. So I could create a new buffered output stream and wrap the stream in that. If I now delete the two files, execute, and refresh again, you will see that we have this new zip file, and we've introduced buffering at a local level that is inside the function, but it still works the same way, it has the same effect, and we did not have to change main to do so. Okay, so that was the built-in libraries. Let's see if we can build a decorator pattern ourselves, and let's use the text field example that I used in my drawings. Let me first explain our starting point. I have an interface that I called graphical component that has two methods, paint and add content. I have a class that I called text field that implements the graphical component interface. It has a paint method where it prints out a set of lines that I've implemented in a simple linked list. And I have an add content that allows me to add strings to that list of lines. It's a very simplistic implementation, but it will do for the illustration of the decorator pattern here. And finally, I have a test class that I just called main. It has a constructor method that just constructs a text field and populates it with a poem from H.C. Andersen and returns it. And then finally, the main method itself just calls that construction method and calls paint. And if I execute that, we'll see that the graphical component or the text field just prints itself out using the paint method. Now, what if I wanted to introduce the border to the text field component? And let's do it right here. In early object-oriented design, someone might have suggested that you create the subclass of text field that is called text field with border, but we don't want to do that. We want to use the decorator pattern. So the first thing I'll do is I'll create a new class that implements the graphical component interface and call it decorator. It will be an abstract class. I will implement the paint method by simply forwarding to a next component. I'll have to add that as a variable to the class. This forms the chain that we talked about while I was drawing. I'll also create a constructor that allows me to initialize that next component. The design here dictates that any subclasses of decorator, so that would be the border decorator that we're creating now, will have to call the paint method of its superclass, which would be this decorator method, so that it will forward to the next component. I will eventually come back to the add content method, but for now I'll leave it alone. Next, I'll create the border decorator. This will be a class that extends the decorator class. I need to override the paint method, and I have to make a decision of how that is going to work. I could render the border before I call super's paint method that will forward to the real component, or I could do it afterwards.
But just for this example, I'll make a print statement in both places. Because I created a constructor on the decorator that requires the next component, I'll have to implement the border decorator's constructor too by simply calling the super next. That should complete the implementation of the border decorator. We can go to main and inject it. The way to do that would be similar to what we did in the IO example. We need to wrap the text field into a border decorator. If I now execute, we should see we get the messages from the border decorator before and after the rendition of the text field itself, as by design. And the printout show could have rendered here, which was what we decided to do before we call superpaint from the border decorator. Then we get the paint method from the text field. And then finally at the bottom we have should probably render the border here, which was the last message we printed out after we had forwarded to the next component from the border decorator. Notice how the borders now have become an orthogonal concern or an independent concern where we can apply a border to any of the graphical components that we might introduce in the future, whether that is a picture, whether that is a button, or anything else. The decorators are simple if the client is the one that actually introduced the decorator. It gets a little bit more tricky if it is the component hierarchy itself that has to introduce the decorators. And we'll see that in the example for the scroll bar. So let's take a look at that. With the scroll bar, we want to introduce the scroll bar if the number of lines cannot fit into whatever text box we have, which means we have to go to the text field's add content method and try to introduce it there. I'll just use some simple logic here. If the line size is 2, we want to introduce the scroll bar. And I'm just going to put a comment in for now. The problem we have now is that the client would not know that we want to add the scroll bar decorator. So how can we actually inject the scroll bar decorator in front of the text box? Or in this case, maybe even in front of the border before the text box. How can we do that? Now, using dynamic proxies and perhaps AspectJ, I could do this very elegantly, but for now, I'm just going to show you an example of how it can be done. So one of the things I could do is I could have the add content return a graphical component. And I can do that by refactoring in Eclipse. So I'm just going to refactor the method to make sure that the add content returns a graphical component. Now it would be possible to implement add content in a way where we return the scroll bar decorator if we need it. If not, we just return ourselves. So I'll change the algorithm here to say when we have 2 lines, I'll return the scroll bar decorator and then pass in this as the next component. The second one, if there's not 2, I'll just return myself. Now I need to implement the scroll bar decorator. Use the Eclipse quick tip to do so. I'll create a new class called scroll bar decorator and make sure that it extends the decorator class that we just created. I'll override the paint method and simply just print out render the scroll bar before we call the next component's paint. And of course, we need to implement the constructor to ensure proper initialization. And again, we have a very simple implementation, but it illustrates the pattern, and I don't want to make it too complicated. We also need to implement the add content method on the decorator, and I'm going to simply just return this. The changes I did has an effect on the client, unfortunately. So now I need to go back into main and ensure that every time we're adding content to a component, we also reassign the variables, often called fluid design, and more common here would be to do tf.addContent and .addContent, and so on. But I'll just make it simple here and introduce this reassignment in every statement. If I now re-execute this class, I will see that I have indeed introduced the scroll bar. You see, we first could have rendered here, then render scroll bar, and then the rendition of the text field. And then we get back to the end statement that the board decorator was doing, just as we expected. To make sure that this works, we should probably also create a 2-line poem. I'll do so by simply copying the existing creation method and construct one called construct2line_tb. I'll use the 2-line version from main, and then I'll execute again. And again, I get the scroll bar, and this is because I made the algorithm such that if it was 2 or more lines, we would have the scroll bar. But I'll change the algorithm so that it requires at least 3 lines. So I'll go back to the text field and change the boundary on where we introduced the scroll bar to 3. And if I now go back to main and execute, we see that if we have only 2 lines now, we don't get the scroll bar. For more than 2 lines, we get the scroll bar. It was dynamically introduced now within the component hierarchy. A contrived example perhaps, but it shows that that is also possible. And again, I would rather have used something like Dynamic Proxy or AspectJ to implement that part of the decorator. In this session, we'll take a look at the facade pattern. Facade is one of the best known patterns, also one of the most misused patterns. What I'll do in this session is I'll introduce the facade pattern using a general example. I'll also show how the facade pattern can be applied to a domain object. And then I'll warn you against bad uses of the facade pattern. I won't implement anything in Java in this because there is really nothing special about Java and the facade pattern. When you study a traditional object-oriented system, the domain model is often where you find also the behavior. That is, you have some arbitrary object graph. It can be very complex. And as a client, it's very difficult for me to know exactly where I'm supposed to go to invoke a function. This particular problem was prominent in languages such as Smalltalk, for instance, where you had that. But you also see it pushed today towards more domain-driven object structure or behavior-rich domain models, as they're often called. So the question for the client here is, which one of these objects am I supposed to invoke to get some business functionality done? In these situations, the design pattern facade can come to our aid. The idea here is to make it very easy for the client and provide an interface that is specifically designed for their use case, or maybe for a set of use cases. That takes away the ambiguity as to where to go or which is the correct object to invoke to get some business functionality performed. All we need to do as a client is to look at that one object, namely the facade. The introduction of a facade has 2 main benefits. One is that it makes it easier for the client. It gives the ones that build the implementation a chance to refactor without affecting the client. Let's take a look at another example also. Here I have an editor which has a clipboard, a canvas, shapes, and I'll just build a simple type model for that. Now the details of the class diagram here is not that important, but just imagine at runtime, if someone wants to use this editor framework, we would have an instance of an editor, an instance of a clipboard. There might be a set of shapes on the clipboard. The editor may have multiple canvas. Perhaps one of them is the current canvas that they work on, and the canvas would have a shape. There would be a complex object graph existing at runtime. The various classes would also have behavior. So for instance, perhaps the clipboard has a copy method that clones all the shapes on the clipboard. Perhaps the shape has some polymorphic create method, static method on the shape. And then we have perhaps a select method on the shape that allows the shape to show its outline that it is selected. And let's also say that the canvas has a select region method. Now, if I'm a client using this framework, I might find it hard to use. I don't know exactly how to get to the various objects, and I need a full understanding of the underlying domain model that was created by the designer. And also that it's too hard to figure out which object to send a message to get some business behavior performed. In this particular situation, it would be natural to try to find one of the domain objects and have it play the role of a facade. In this particular example, I would probably have chosen the editor as it knows where the other objects are. It's a natural API for the client. So I would elevate the methods on various objects within my framework and put them on the editor. Let's start with the clipboard. The copy method, I would put that in the editor. Now, the editor wouldn't do the actual copy work. All it would do is forward to the clipboard. Another method that we might want to lift to the facade is the select region method that is currently on the canvas.
Now the editor would have to do a little bit of work here. It would need to know exactly which is the current canvas, but that would be a natural thing for the editor to do already. So what we would do is basically just have it find the current canvas and then forward the message of selecting a region to that canvas. We're taking all the methods that a client might want to invoke on objects within the framework. We're lifting that to a single object that the client can use. And notice in this case that I've picked a domain object, a natural object. And I love it when I can do that with the facade. However, sometimes that is just not possible, and we may have to create some kind of API for the facade. But if there is a natural domain object, that would be the best choice in most cases. Here is a bit of warning though. Sometimes designers claim to be using the facade pattern when what they really are creating is a monolithic monster object, God object. The idea of the facade is for it to be very light. What it's trying to do is just be an API. It's trying to look up the right object to send the message to. I think it is an anti-pattern when the facade starts having a lot of business logic. That could happen if the facade is a natural domain object, but at least its facade part should be very light. A traffic cop that simply forwards messages to other objects. In this section, I will do something quite different from the other sections. I will not introduce any new patterns. Instead, I will compare a few patterns that designers often confuse to help you name and select the right pattern for your design problem. In the previous sections, we've seen a few patterns that at first glance look quite similar. In all of these patterns, we introduce some object that sits in between the client and the target object. The client invokes a method on the introduced object, and then the introduced object forwards the message to the intended target. The introduced objects may execute some code before and after. These patterns rely on a concept called delegation, and there are at least 4 of these patterns that I've often seen designers confuse. The 4 patterns that we covered that are often confused are called proxy, decorator, adapter, and facade. Some are more commonly confused than others. If we make a comparison table, it's easy, at least at first glance, to see how some of them can get confused. Let's first take a look at what the object structure might look like at runtime. First, we have the proxy, where a client wants to talk to a real object, but it does through a proxy. And that proxy may forward to another proxy, so we might have a chain of proxy before we get to the real object. Although it's rare that we have multiple proxy, it can occur. What is interesting here is that the client often have no idea that it's working through a proxy, and that the real object and the proxies often have identical interfaces. When we look at the decorator, it also looks very similar in the object structure. What a client does is it typically talks through an object that we call a decorator and forwards to another decorator, perhaps before we get to the real object. And at first glance, these seem identical, and that's also why they're most often confused. But the decorator here is a little bit different, as we'll discuss. First of all, often the client knows that it's talking to a decorator. It might actually be the one that instantiated the decorator. Looking at the runtime object graph for an adapter, we see that the client goes through an object before it gets to some other object again. We call the first object they interact with an adapter. And often what they're talking to is some legacy component or some component whose interface doesn't quite match what the client wants to see. So we can clearly see here that there is at least one difference between the proxy and the decorator, that the interface to the client is different from the object that the adapter adapts. So the client has an expectation of an interface that is different from the one that is on the object that has the implementation. Now finally, we have the facade, which is quite different than the others. We have an object that forwards to a set of other objects. There's someone that is basically simplifying an object graph. Next, let's take a look at what it looks like in the class structure for these 4 different patterns. The proxy pattern, a client uses some component interface. It may be using a proxy, it may be using the real, the client doesn't really know. Typically the proxy and the real object implement the same interface, and the proxy has some reference to another component interface, which may be the real or another proxy. When it comes to the decorator, it looks almost identical to the proxy in the class diagram. We have a client interface, we have some real object that we want to decorate, and we have a set of decorators then forwards to the client interface. It's typically part of a framework that the client knows about, and we expose to the client the various variations of decorators that we have. We can clearly see some differences in the adapter to the decorator and proxy. A client uses a component interface implemented by an adapter, but that adapter forwards to another component that is typically not related to the client interface or the component interface, by inheritance at least. And looking at the class diagram for a facade, we clearly see that that's very different. A client uses a facade that may have been one of the domain objects, but often it's an introduced object, and the facade then forwards to a set of other objects, and it's trying to hide the complexity of the underlying implementation from the client. Although it's very difficult to see the difference between the proxy and the decorator, the adapter and facade has some clear differences. The adapter has this association to a LC here, legacy component typically, that is not linked through inheritance, it's simply a forwarding mechanism. So we can clearly see that that is different from the other patterns. And on the facade, we see that the client uses a single object that then forwards to multiple objects, which we couldn't see in the other object, or typically a single other recipient from the object introduced between the client and the implementation. So just to summarize, when it comes to the facade, the difference is usually clear as soon as people think about it a little bit. The goal here is to hide a complex structure and make it easy for the client to use a framework or a complex object graph. The adapter may be slightly more difficult to see. The difference here is that the client is using a different interface than the actual implementation, and it's about translation of interfaces. Coming to grasp with the differences between the proxy and the decorator pattern is much harder. What we can say about this is that the decorator is often part of a framework where the client is aware of the design. They may be the one that instantiate the decorator, they may be the one attaching it. But that's not always the case. Sometimes the components themselves introduce the decorator, but it's often much more clear to the client what is happening. In the proxy case, what we're usually trying to do is we're trying to hide the proxies from the client, where the client is using an interface that is clear to them, in most cases not even aware of the fact that the proxy is sitting in between them and the real. And it could be to do remote communication, it could be to check security, for instance, things that we don't necessarily want to implement on the real object nor on the client. And there's often also a single proxy involved. While I drew the comparison table, we saw that the facade and the adapter patterns are quite different. However, the difference between the proxy and decorator patterns are harder to spot. Perhaps they should have been the same pattern. Some designers would argue for that. But I think the Gang of Four did an excellent job in picking the patterns and arguing for why one is different from the other. It is my experience that having both patterns and being able to distinguish between them is quite useful when discussing with other designers. There have been cases in my design when I introduced frameworks where the proxies and decorators are mixed. But when I do, I try to name the classes that implement them decorators or proxy based on their main purpose. The following table shows how I make the distinction. One dimension is if the client is involved in the creation or construction of the delegator. In the case of proxies, it's usually my goal to make sure that the client doesn't know that it's using a proxy, or I try to introduce it without their knowledge. In the case of the decorator, that's not always true. Often by design, I allow the clients to add decorators. So the typical purpose of the proxy is to overcome some main hurdle that neither the client and the target should be aware of. This could be, for instance, distribution, where we have a remote proxy. It could be a security, where we need something to be checked. But we don't want the ones that implement the service to have to deal with security or distribution, nor do we want the client to worry about this. In the case of the decorator, It is more a goal to implement orthogonal concerns that are usable across a set of components as part of a framework. At least this is my guideline. Others may have slightly different guidelines. It probably is a good idea for you to go back and reread the patterns in the book, or also see discussions online of how people separate the proxy and decorator. There are differences in opinion here. This is my decision table. In this section, we'll take a look at the Creational Patterns catalog from the Gang of Four book. The Gang of Four book has 3 sections, and one of them is dedicated entirely to the creation of objects. They describe 5 different patterns that help insulate the clients from the complexity of creating objects. Java provides mechanisms to help with creation of objects. So some of these patterns may not be as useful or as common as they used to be. However, it really helps to know the Gang of Four pattern, and it's still valuable, and often you will see the vocabulary of the Gang of Four being used in various sections of Java frameworks, such as Spring. The 5 patterns that the Gang of Four identified was the abstract factory, which is a way of insulating the client from some external factor that determines what family of classes to use. External factors can be which operating system are you using, perhaps some context, is it day or night? You might want to create different objects based on some external factor that the clients are not supposed to know about. This may still be practical for some special applications and frameworks. There is also a pattern called Builder, and this is a programming idea that is often used in Java framework, and we're going to take a look at that in more detail. The first one we're going to actually look at is the one that's called factory method, which is a very common way of creating a factory for creation of objects. We also have a pattern called prototype. It's a pattern that allows for creation of objects based on cloning. And it's very practical in applications where you want the runtime user to configure how to create some objects. And finally, we have Singleton. This is a pattern which seems to be the most known of the patterns. This pattern is used because there are some objects in our domain, there should be only one, and it really should be present from the very beginning of a program, sort of where the main starts. And the Singleton pattern is suggesting a way for us to manage that. So what is the problem about creation of objects? Well, there are several, but the more common one is the fact that we can't have a polymorphic constructor. We often rely on polymorphism to shield the clients from an implementation hierarchy, so that they can have a handle to something abstract like a shape, and when they call a method on that shape, say draw, the correct implementation is picked by the runtime environment based on what kind of shape they're having a handle to. However, this doesn't work when creating objects. Whenever we're creating objects, say from an input stream, we can't just call shape.create, because to take advantage of polymorphism, an object must exist. Now, there are some languages that have polymorphic constructor or have features that makes it easy to do this, like Smalltalk or Objective-C, for instance. However, in Java, we can't do this without some trickery. Let's dig a little deeper into this fundamental creational problem that we have in some object-oriented languages. Let's assume we have a hierarchy where the most base type or interface is a shape that has a draw method. And we have a couple of subclasses of the shape, a rectangle and an oval. And they would, of course, have their own draw methods. Polymorphism allows us to hide the complexity of the hierarchy or hide the various subclasses from a client under normal use. So say, for instance, I have a client that gets a list of shapes that they need to manipulate. They don't need to know what the exact implementation of those shapes are. They can get a list of shapes, go through each shape, and draw them without knowing whether the first one is an oval or a rectangle or in what order things came. So polymorphism, wonderful if the objects already exist. But what if the client had a file where various shapes that we want to create have been serialized. So our goal is to read that file and instantiate a set of shapes. And they may come in a form where we have some tag, maybe pound rect means rectangle and pound triangle means triangle and so on. Now we may end up burdening the client with knowing exactly the format of this file, this external context if you want, and how you map that into the correct instance or the correct class that creates the instance. For some languages that support polymorphic construction, this will be trivial, but Java is not one of those. So the typical clever solution here is that we have the client read the file and get the content, and then delegate to some other object that we often call a factory that will then create the correct shape for us. Now, after that has been created, we can use that shape without knowing exactly what the string in the file mapped to in the implementation hierarchy. That means that the factory, or the object we delegated to, knew that the string mapped to a rectangle. However, we only use the interface shape, so we don't have to be burdened with the concrete subclasses or any knowledge thereof. So the reason for this delegation is that we want to take away the responsibility of mapping an external context, here the pound rect, for instance, into the correct implementation class. Creating objects of type shape requires that someone maps the strings in the files into the correct class, and also, of course, the parameters or the rest of the string into the proper parameters to the constructor. We don't want the client to have to be bothered with this. Let's take a look at a trivial example where the client has been burdened with creation. In this example, I have a main where I have an array of strings. I create a client object, and I ask that client object to read the shapes from that array and then draw out all the shapes. And we see that the string that represent the shapes have to be mapped into the creation of the correct object type. We see that this is a working application. If I run it, we get as an output drawing a rectangle and drawing an oval, which maps to the strings that we passed into the client. The creation is dynamic, so if I add another rectangle to the array of strings and run it, we'll see that we get another rectangle created also. And if we open the client, we will see the use of polymorphism, but also a suboptimal algorithm for creating objects. Now, the first thing we notice is that we have a list of shapes which have no knowledge of the various subclasses. It's a list of the abstract type shape. Then, when we draw the shapes, we're taking advantage of that, and we're simply looping through the shapes and telling each shape to draw without knowing whether it's a rectangle or an oval. We were not able to take advantage of polymorphism in the read shapes, though. Here we have the client that is mapping the pound rect to the creation of a rectangle or pound oval to the creation of an oval. In other words, polymorphism doesn't work for creation of objects. When we create an object, we have to know exactly what class we're creating. Now, this is a huge problem. Let's say we introduce a new kind of shape, say a line. What will happen now to the clients? All clients that is involved with creation of object will know how to change their algorithm. Let's say, for instance, in the example we had, we add another shape, a line as the last item. For that to work, we would have to go into the client and change its code. That means that we have a really bad isolation of change. The introduction of a new class into the hierarchy of shapes requires change to the client also. So in this example, I need another clause to this if-else statement that looks for a line and creates a new line. Now you can imagine if we had several clients, they would all have to change because we introduce a new kind of shape. If I run the program now, it will correctly create the line as we see, but we don't like this. If a change requires changes to the code in multiple places, that's a suboptimal design. So what we want is to move this knowledge of this mapping away from the client
and into the shape hierarchy. What the factory method pattern suggests is that we move it in as a method on the most abstract type. And from Java 1.8 and onwards, you can add a method directly to the interface. However, in this example, I'm using Java 1.7. And for that, I need to change the interface into an abstract class to make this pattern work. So let's move the creation algorithm from the shape class into the static method on the base class. Now that we're operating on a single shape, I'll just make a simple return value, and I'll assign the return value to the appropriate instantiation of the class before returning it from this method. Also, because we're using Java 1.7 and I had to do this with an abstract class, obviously I need to change the classes to extend the shape instead of implementing a shape. And we have an error here where I used the wrong variable name when I did the copy and paste. So I'll change the variable name to S, which is the string parameter coming in. And we also need to change the algorithm of read shape now. Since we now have the switch statement or the if then else statement in the class method that we created on shape, we can simplify this significantly. And it looks very much like a polymorphic constructor at this point. The client is no longer burdened with knowing about all the subclasses of the hierarchy, and we have the equivalent to a polymorphic constructor. This pattern is called factory method, and this is when we create a method, typically a static method on the most base class, that is responsible for knowing how to map some external context into the correct subclass in the hierarchy. Now all that remains is to try it out, so we'll run it, and we see that indeed we get the same result, but now with a much simpler client. So the general solution here is that we are taking away the burden of mapping some external context to the correct creation of subclasses from the client by simply introducing a static method on the most base class that does the creation on behalf of the client. That way we can localize all that behavior to the hierarchy itself. So our problem when it came to the factory method is that we had a client that need to create something, and it uses a factory, in our case a factory method, and creates an object passing in a context. The factory could then create the concrete subclass. The client would use a simple interface and not be aware of the various concrete subclasses. So this is our situation. But what if the client can't be aware of the context or is totally unaware of the context? Well, in that case, we want to use a slightly different pattern called abstract factory. And we'll take a look at that one. For illustration, let me minimize this example or this context and copy in a concrete example. In this example, we have a simple user interface library that consists of widgets. The client is unaware of what operating system we're working on. And to make that work, what we've done is we have created interfaces for the common widgets, such as window, scroll bar in this example. We have various implementation here shown with an X window versus a Microsoft window, X scroll bar versus a MS scroll bar. But our hope is that the client can use only the interface and be unaware of the operating system. To achieve this, we will introduce a widget factory. The widget factory will have an interface such as create window, create scroll bar. But the widget factory is just an interface. We will have various implementations of the widget factory. We would have one for creating, say, X windows, and it would have to implement the create window and the create scroll bar. And when we call create window, it will create an X window. When we call create scroll bar, it will create an X scroll bar. But the client can use this widget factory without knowing what kind of window will come back. We call this pattern abstract factory because we have introduced an interface, the widget factory, that has various concrete implementation, the widget factory being the abstract factory. Let's try to abstract this and take a look at this from the Gang of Four patterns view and introduce the right roles. Here I've copied in the abstract solution to the pattern. And we see that we have a client here up top right that creates object using the factory.
Now, the factory, we will have only one implementation based on context typically. So we create one of the concrete factory, and through polymorphism, we'll pick the right creation method associated with the correct product. We had various kinds of widgets in our example. They call them products. So the client can then simply use the products interface without ever knowing the concrete implementation. So we basically have one factory that has been instantiated to create a family of objects based on some external context that the client is unaware of. Let me quickly go over some of the other patterns also, and I'll start with the prototype pattern. The prototype pattern is very useful when we want the client to configure how objects are created. Let me introduce a client here whose purpose is to configure objects upon creation. So they want to determine how other clients create a particular kind of object. And I'm just going to call it the configurator. The prototype pattern suggests a very clever way to do such a thing. What you do is you introduce a shape that will act as a prototype. This shape's sole purpose is to be an example for other objects that we create. We have this familiar hierarchy that we've seen before with a shape as a base class and, say, a rectangle as a subclass. The actual prototype shape would, of course, be one of the concrete subclass types. So this prototype here could be a rectangle, for instance. The configurator will simply manipulate this shape and set the color, set the border width, or whatever properties they want to make this the default setting for all creations of rectangles. The way other clients would create rectangles now is by simply calling a method on the shape that acts as the prototype and ask that shape to clone itself. As a result of that, a copy is created by the prototype that has the exact same configuration as itself. And now a client can simply start using that copy. Because the clone method is polymorphic, we can now have the client basically talk to a shape that knows to be just one of the prototypes for a shape and use polymorphism to pick the right subclass. Now you see this in tools like Visio. If you're on Microsoft, you've probably seen this, where you can grab a shape from the toolbar, and the toolbar is unaware of what kind of shape it is. And when you pick one of those tools and drag it and drop it onto your canvas, what happens is that the toolbar or the environment will call clone on that example object that exists inside the toolbar. So a very clever little pattern for creation. We call this pattern prototype, and let's take a look at one more pattern. Let's imagine that we have some object that we need to create that is very complex. It may have a set of properties, or it may have a complex information model sitting behind it. Now, for a client to construct such an object is quite difficult. They have to have very intimate knowledge of how the object is constructed internally to be able to create a constructor with the correct parameters or pick one with the correct parameters. So in short, our problem is we want to construct something that is very complex. The builder pattern suggests that in these cases that we introduce a special kind of object whose sole purpose is to aid the client to configure the complex object. As the client invokes methods upon the builder would know how to configure the complex object behind the scene. And we can make the builder interface very easy for the client to use. It could have things like set X, set Y, very simple methods. And finally, when the client has finished the configuration of the object, they call a method on the builder to get that object, which is now fully initialized. We call this pattern for the builder pattern. Now, I want to point out that for both of these patterns, in particular the builder, I recommend that you read the patterns book to get more of the details. There's a ton of tricks with the builders that are useful. For instance, using what's called a fluent interface so that you can chain the configuration commands. And there's a ton of other things that probably would be useful, but I just wanted to give you the general idea of the builder. So we're now seeing the factory method, the abstract factory, the prototype, and the builder. And the only one that is left of the 5 patterns that makes up the Creational patterns catalog in the Gang of 4 book is the Singleton.
And I'll show you that one also to wrap things up.
Well, that wraps up this section on how to use the creational patterns. We've seen 5 creational patterns that were in the original catalog: abstract factory, builder, factory method, prototype, singleton. They're used for slightly different purposes and should be part of your design vocabulary. I've mentioned in a couple of places that things like injections and so on have maybe changed this landscape a little bit, but I think it's good to know these patterns and ensure that you know when they're used. Well, that was creational patterns in Java. I'll see you for the next section. In this section, I will teach you the pattern called observer. The observer is a very influential pattern. Many languages and frameworks have come up with their own variation of the observer, but it's good to know the original idea. In this lesson, I will first show a problem where the observer pattern would be a good match. We'll generalize that problem, apply the observer pattern to it, and then I'll generalize the problem into a form of a pattern. And then we'll look at how the observer pattern can be implemented in Java. And it turns out that in Java, there is, first of all, some support for the observer pattern, but there is also a variant way of doing the exact same thing as the observer pattern is suggesting, which is part of this Java beans idea. Let's say we have created a device. This is some kind of thermometer that can measure the temperature in ambient environment. And we're really excited about this. It's very cheap to produce and so on. We want to write some code that allows any buyer of this thermometer to hook it up to a machine, being a Windows, a Mac, or whatever. So we need to write some kind of driver that can read the temperature outside and feed it back to their application. In addition to the driver, we'll create a thermometer object that allows the applications to read the temperature outside. At minimum, it will have to have this getTemperature method. Now we can wrap this up. We can sell these devices on the internet. We have the driver that they can install, and we also have some software that makes it easy to access the thermometer. It would be easy for any client to read the temperature at their leisure. However, what would be tricky is for clients that want to know exactly when the temperature changed. They may have real-time requirements that force them to take some action whenever the temperature changes outside, and they may have very tight deadlines. The problem now, of course, is that for us as the writer of the thermometer object to be able to send a message to the client in a standard object-oriented language, we would need to know who they are. We would need to know their interface, what method they want to call. The only way that will work is if they call us and ask for a custom thermometer, but there is a better way. The most common solution to this is that we ask our clients to be polling us. That is, they will go and ask get temperature at a regular interval. But then the question is how often? And it also seems quite wasteful. And even if we polled, say, every 10 milliseconds, even that 10 millisecond is an average delay of 5 milliseconds from when the thermometer knows that the temperature has changed. So ideally, what we want is for the thermometer to send a message to the client with the new temperature. However, our problem is that the thermometer cannot know about the client itself. And this is exactly where the observer pattern might turn out to be extremely useful. Let's see if we can come up with a solution to this. Assuming we have the thermometer, and let's say the driver gives us some feedback whenever the temperature on the hardware is changed. We need to implement this, and what we want to do is set the new temperature and then go to all our clients and tell them that change has occurred. But how can we ensure that we find all those clients that are interested, and what can we tell them? If this is going to work, we need the following to be present. So all my dependents have to be of type client, or some type that I can predict. The client types must also understand the changed occur method, or whatever we decide to call that method. Doesn't seem like we've solved anything, but let's see if we can follow the following set of rules, or if we can implement it in this way. The first thing I'll do is to introduce an interface that all dependents must implement. The reason for the introduction of this interface is so that the thermometer can hold a collection of references to clients of the same type. I'll call this interface Observer. Next, we need to implement some kind of registry that allows the thermometer to keep track of all the observers, that is, all its dependent objects. And I will also implement the registration behavior in a reusable class that can be reapplied to other objects that may have dependents. And I'll call that class Observable. Well, that completes my plan. So what will such a solution look like? Well, let's start with the interface that we want the clients to implement. We call that Observer, and we need a method that we can call when we have discovered a change, and I'm just going to call that Update. Next, I'll focus on the reusable class that has the registration behavior, and I'm going to call that class Observable. The registration behavior would be two methods, one for adding observers and another one for removing observers. I'm also going to create the convenience method that is protected that allows the subclasses of observable to notify all its dependents. So now all we need to draw in is the association where the observable is keeping track of a set of observers. What we created now is a totally generic way of having dependencies taken care of. That is, we have an interface called Observer, which can be implemented by objects that want to listen to changes on other objects. And those objects that are being listened to would have to extend the class Observable and therefore get this behavior of adding and removing observers or registration of observers. We also introduced this convenience method called notify dependents so that subclasses of observable can invoke this method, and the observable class would ensure that all the observers that are listening are informed. And if no one is listening, then of course it will be a no operation. And now we need to plug in the example classes. So first we have the thermometer, which we will make a subclass of observable. When we created a thermometer, we don't really know who our clients are, but let's just assume that we have some thermometer client. That thermometer client will have to make sure that they implement the observer interface. There may be many of these clients of different types, and the point here is that the thermometer doesn't really need to know. All it knows is that it will extend observable and call notify dependents whenever it has a change. The work for the thermometer now is quite simple. If we have a method, just call it driver update, whenever the driver updates the thermometer, all it needs to do is assign the new temperature and then call its supertype and say notify dependents. All the knowledge of dependencies and who's registered, who's not, exists on the superclass, and the thermometer's implementation becomes very simple. For completeness, let's also show the algorithm in notify dependents. All it would do is go to all of its dependents and call update and probably pass in this or the object itself so that the observer, in this case, some thermometer client, knows which one of the thermometers have changed, perhaps so you can go back and ask the temperature. Now, it might be hard to see what we're doing in a class diagram, so let's take a look at this in a sequence diagram. First, we have the thermometer client. I'm just going to call it T client. Next, we have the thermometer. Now, I'm going to use a non-standard UML construct here, but I want to show the protocol between the superclass and the subclass. And the thermometer can be split into two parts. There is the subclass thermometer and also the base class observable. As I said, this is a non-standard UML. There's really only one thermometer, and it really should have been only one lifeline. The first thing that happens is that the client calls the thermometer and says add. Now that method is intercepted in the base class. That's why I'm drawing it to the base class part. It would do that by simply calling the add method on the thermometer, passing itself. The observable base class will now store a reference to the client. At some point later, the driver has discovered that the hardware outside has changed temperature, and it will call the thermometer and say, here's the new temperature. The thermometer changes its state by setting the new temperature, and after that, it calls the base class to have the observable implementation notify its dependents. So the last statement in the recipient method from the driver would simply be super.notify dependents. Notice here that the thermometer doesn't really keep track of dependents and doesn't know if there are 100 dependents, 1 dependent, or 0 dependents. All it's responsible for is to make sure that the superclass notify dependents method gets called. The superclass observable will now call all of its clients, anyone that's called add, haven't subsequently called remove, and call it with the change method. That method, I think I called it update. The algorithm here is pretty simple. It's basically go through the collection of references to dependents and invoke the change or update method. And often here we pass on the this pointer so that the client knows which object has changed. Now the change method here could be whatever the client needs. All we have done is we basically activated the client. We've given it a chance to run at the time when the temperature changed. Now, this pattern has become a very popular way, particularly in user interfaces, to have model objects that then change, and then whenever a change occurs, the change is propagated so that UI widgets can be updated. But you can use it in any other context also. Let's look at this pattern in code. I've prepared an example here that we can use and refactor with the observer pattern. I'll explain this one by going through the various components. The first thing we need to look at is the thermometer. And the thermometer has a temperature that it keeps track of, a temperature in Kelvin. It has a few constants that shows me how to format it when I'm printing it out. And we have just a little bit of implementation. One is a callback method that comes from the driver. So this is a new driver value. And just to make it simple, I just took the driver value and divided it by 100. We said that is the temperature in Kelvin. And then we have a few accessor methods that give me the temperature in various formats or in various units of measure, Kelvin, Celsius, and Fahrenheit. Next, let's look at the driver implementation. It's not that important what we're doing here, but it's basically a simulator that produces events and calls the thermometer's driver value at regular intervals. And I have a few configuration parameters that allows me to play around with how often I create an update and also the range in which an update can occur, how many degrees up and down it can go if you want. I made the driver a subclass of a thread. That means it has its own thread running. There is a run method, but really the critical piece is that at some regular intervals, it will call a thermometer and say, here's the new driver value, and pass in some value that fluctuates up and down. I also created a setup class. This is basically just a convenience class that sets up the experiment. In the constructor of setup, I create the thermometer. I then create the driver and pass in that thermometer, and then I start up the driver. There is also a method for clients or those that have access to the setup to get to the thermometer itself. And finally, I have a simple shutdown method that allows me to close down the experiment. Finally, I created a simple client to test this out, and I call it the polling thermometer client. Nothing special here either. There is a constant that I've created that allows me to say how long I want to run in seconds. There is a constant for saying how long between the polls that I want to achieve. So that would be 50 milliseconds here. I usually run with 100, but right here I run with 50. I create a setup. That's the one that creates the thermometer. So I need to grab that thermometer from them. But it's useful here to see the symmetry. So the setup has a corresponding shutdown. I grab the thermometer, and then I basically just calculate times through the loop I have to run for that 20 seconds in this case. And then there is basically just a loop, and all it does is it sleeps for X number of milliseconds, and then it goes and asks the thermometer what the temperature is. In this particular example, every 50 milliseconds. And that's kind of the completion of this test client. Now let's run the polling thermometer client and see what happens.
The system will now start to print out the whole set of messages. I'll freeze the frame here so we can see it. And we see, for instance, in this example, that we only had 4 driver updates, but we've been checking the temperature 101 times. We're printing out a ton of checks. In fact, there's about 400 of them. And the driver has actually only updated 11 times. This is obviously a complete waste of resources. Let's illustrate what's happening with a simple drawing. We have 3 objects in play here: the driver, the thermometer, and the client. Obviously, we also had the setup, but it's not really important for now. The driver has its own thread that I'll draw in red here that sends out the driver value message to the thermometer. The way we have it set up, it will do so about every 5 seconds on average. The client is using the main thread, and I'll draw that in blue, and the client uses this thread to go and ask the thermometer for the new temperature. Because the client doesn't know when the driver has updated thermometer, it basically is forced to do a whole set of polling. And it does so actually in our example every 5 milliseconds or so. Apart from being annoying, it's obviously a waste of resource, but it also has latency that is unnecessary. Depending on how frequently we poll, half of that interval between 2 polls is our latency. So if we poll every 100 milliseconds, we would have a latency of, say, 50 milliseconds. So not only do we waste resources, but also we have a latency that is suboptimal. So let's try to fix this by applying the observer pattern. The first thing I'll do is I'll add an interface that I'm going to call the observer. The observer will have a simple method called update, and I'll give it parameters later. Next, I'll create an abstract class that I'm going to call observable. The observable will have to hold the registration behavior. This is where observers will register themselves for updates. I'm going to make a set of observers. Probably could implement this as a list. I'm going to make it a set, so I make sure that observers are not added twice, so they go multiple updates. In some cases, you may want this to be a list if you want to guarantee that dependent objects or the observers are called in a particular order. But I don't really want that behavior. Next, I'm just going to add a couple of accessor methods that allow you to add observers and remove observers, or register yourself as a dependent and remove yourself as a dependent. I will also add a constructor to make sure that the collection of observers have been created prior to use. And finally, I'll create a protected method, meaning a method that can only be called from the subclasses, that I'm going to call notify dependents. All that is doing is it iterates through all the observers and tell them to update. Now, I told you I would come back to the update method's parameters. And what I want to pass on as a parameter is basically the observable object. So I'll fix that in the interface and also then pass on myself when I call the observers. Now that we implemented the observer and the observable, we can go back to the thermometer and make sure that that extends observable. That is going to be the observable object. We also have to make sure that when the driver tells us that there is a new temperature, that we notify all our dependents. And we do that by simply calling super.notifyDependents. So what will happen now is anytime that the driver gives us a new value, we will set the value and then we will broadcast that change to anyone that is listening. And that behavior of broadcasting is happening on our base class observable. Now let's create a client that works with the observer pattern. I'm going to start by copying the polling thermometer client so we can see the refactoring. I call the client observer thermometer client, and I have to make sure that it implements the observer interface. We then have to implement the update method. I'll simply copy the print statement from the previous main into the update method. The print method depends on a thermometer called T. We know that the observable coming in is a thermometer, so we can simply cast it to a thermometer. There is no reason for us to keep track of times we call it anymore, so I'll remove that. I'll create a constructor, and perhaps I should pass in the setup to the thermometer client. I'm not sure I absolutely need that, but we'll see. I'll add it for now. I don't need these constants anymore, I can delete those. I'll create a new observer thermometer client in main and pass in the setup. And we can remove most of this algorithm. Probably all we need is to sleep for, say, 20 seconds until we shut down the experiments. And right now I can't see why we need to pass this setup to the thermometer client, so I think I'm going to refactor that and remove the need for setup. I have a warning here that I haven't used the variable client. Probably need to use it later, but for now let me just suppress the warning. Now let's see if it works. Let's try to run it. When we run it, we see on the console that we do get the driver updates, but we never get the temperature printed out. And this is because we forgot to register the observer client with the thermometer. Someone needs to add the client as a listener to the thermometer. I can do it here in main. We could, of course, have done it inside the client also. Now that we're using the client variable inside main, we should be able to remove that suppress warning. We'll run it again, and we now see that we're getting one printout for every driver update with no latency. As soon as the driver has an update, the thermometer calls its dependence, the thermometer client prints it out. So for the observer pattern, if we generalize the problem and forces, we have the situation where an object must communicate to an unknown number of dependent objects a change that occurred to it. And perhaps these dependent objects are not known. We don't know who they are. We don't know what type they are. It is not possible, or it may be undesirable, to have the changing object directly talk to the dependent objects. The observer pattern suggests a solution to this. In this solution, the object that needs to inform other objects about the changes is called a concrete subject. So we had the thermometer in our case. It subclasses a library class that in the observer pattern is called subject. Now we called it observable to be compliant with the solution that we saw in Java. There are methods to deal with registration of observers. So attach and detach is what the design pattern suggested. We call them add observer, remove observer, which is also what Java called them. And there would be a method to notify all the dependents, typically called from within the concrete subject itself, but sometimes it's actually good to have that method called from the outside. The subject class can be a library class, and it keeps track of all observers. Observer would be typically an interface in Java or an abstract class in some other languages. It would have a method that is not implemented on the observer, but implemented by the concrete observer. In our case, that was just an observer client or thermometer client. The observer class or interface will also go into the library typically, because this is a completely generic decoupling mechanism. And the concrete observer would then override the update method and perform whatever action they need to have happen whenever the concrete subject changes. In this section, we'll take a look at the design pattern called command. The command pattern is one of the most used patterns, but I will teach this pattern a little bit different from the other patterns. What I'll do is I'll introduce the command problem in code and do some refactoring of some problem to show how you can use the command to encapsulate functions. And then I'll do a whiteboard discussion of the command pattern by taking a look at Eclipse and the way they use command. Finally, I'll also take a look at some of the new features in Java that improve the implementation of the command pattern. I will use Eclipse to show you this pattern, and I'll start by creating a new class. I'll just call that class for demo and put it in some package. I'll let this demo class be executable by adding a main method to it, and we'll have a very trivial problem. What we want to do is we want to print out the sum of a sequence of numbers from 1 to 100. I'll start by adding the print statement, and then from within the print statement, we'll call a function that we have to write.
I'll create a simple method called sum of sequence that takes a lower and an upper bounds and then summarizes the sequence in between. I'm just going to simply create a sum variable and do a for loop that goes from the lower including the upper and then summarizes them and returns the sum to the caller. What I want to focus on is this algorithm that we created, trying to make that algorithm reusable. Just to make sure we get 5050, let's add the call to the function in the print statement. And I also need to make the function static so we can call it. Now we can run it and we see that indeed the answer is 5050. Now that we've proven that we can do that, let's say someone gives us a different problem. And in this problem, they want us to print out the sum of squares in a sequence. Simply copy the line and say we want now to print the sum of squares from, say, 1 to 10. And as computer scientists, we recognize that the algorithm for calculating the sum of squares in a sequence will be very similar to the one that we did earlier, the sum of a sequence. We do a copy and paste of that algorithm. And after we've copied the algorithm, now all we need to do is to change the name of it to be sum of squares. And also where we accumulate, we have to make sure we accumulate the square rather than just a number. Now if I can calculate that correctly, that should be 385. So we can run the program and we see that indeed it is 385. Every time we do copy and paste of something in code, we should always think twice about it. Alarm bells should come on. Is there some other way we could do this? Is there some way we can capture whatever was common between whatever we copied and the modified code that we wrote? And we see that the two algorithms are almost identical, apart from the function that is applied to the number in the sequence. Now, what if we could encapsulate that algorithm somehow? And the command pattern is about taking an algorithm and making it into an object. Some people would call that reification. I'm just going to call it function object in this case. But it's basically about taking an algorithm and making it into an object so we can pass it around, so that we can have variables that point to it, and so on. You see, the concept of sum of a sequence is reusable if we could just make the function into something. So if we had a sum function that took a lower and upper bounds, and then a function of type f, we should be able to capture the commonality between the two functions. We could now copy the algorithm and simply change the statement where we accumulate to f of I. Unfortunately, in Java, that is an invalid syntax, so I'll come back and fix that later. But assuming that we had such a function, then we could simply, in our call to the sum, pass in the algorithm that we want to apply. So say we could simply just pass in I for the first example and then I times I for the second example. In languages that support functions as first-class objects, that might very well be possible. But unfortunately, that's not possible in Java. So we can use some tricks to make that work. And these tricks are very similar to the idea of the command pattern. We will make a function into an object. So I'll simply use Eclipse refactoring tool here to introduce the interface function. For this to work, we would basically introduce a method apply, so we can apply the function to the value of I. Again, I'll use Eclipse tool to introduce that method to the new interface. For this to work, we will have to use another trick, and I'll use anonymous inner classes to do that here. So I'm introducing a new class on the fly. So I create a new function, and then I'll implement the apply method so that as a client, I can specify which algorithm I want the sum function to use. In the first example, we simply wanted to return I because we're just doing a sum of the sequence itself. I'll do the same for the second example, except now on the apply, I will return the square of the number passed in. And we see the net effect is I can delete the two previous functions and get away with only having a single function for sum. Let's also run it to just make sure that we get the same result. And we see that, yes, indeed, the same result is produced from this, even though we only have one sum function.
So what we did is we took a function or an algorithm and we encapsulated it into an object. And many languages have this idea of having functions as first-class citizens. And for those that are used to programming in such languages such as Lisp or JavaScript or Scala, this idea of taking an algorithm and making it into an object, a first-class citizen, is a very natural thing. So in Java 8, they introduced this concept of lambda expressions that makes implementations of this type of constructs a lot more natural. If you ever find yourself programming in Eclipse to create a plugin or extend Eclipse in one way or the other, you will very quickly get familiar with the idea of a command pattern. Anything that happens in Eclipse, so for instance, if I type something, this gets encapsulated or put into a command. And this allows us to do things like undo and redo. So for instance, if I type something in this editor and then I undo typing, it goes away. And if I go back and do redo typing, it comes back because Eclipse uses the command pattern. And I'll show you how that works. Now, when I undo from Eclipse, invoke it through the menu or use the command key for that, the tooling itself has no idea what was previously done. All it does is go to something called a command stack. The command stack is an ordered collection of commands. The commands encapsulate whatever we had done in the past. So say, for instance, in this case, I did some typing last, then I would have a typing command or insert into editor command. If I had before that deleted something, it would know that the action before that was to delete. And say I did some other stuff before that. So it basically is a collection of commands, and commands being objects that remembers what was done. These are smart commands that know how to execute and do the undoing and redoing on behalf of the editor. What happened in Eclipse when I selected the undo typing is basically a message sequence that goes something like this. The menu item will go to the command stack and simply tell it to undo. The command stack pops the top command and tells that command to undo itself. And using polymorphism, the menu item doesn't necessarily know anything except that it's calling some method on the command stack, or it may know that it's doing undo, but the command stack itself may not know anything about what the various commands are. And it's very easy for you as a programmer to introduce a new command into Eclipse. All you need to do is to implement the behavior required by the interface of the command, which will be undo, redo, and execute. So let's take a look at what that might look like in a class diagram. First, we have the command stack. And the command stack is almost like a facade, if you remember that pattern. The facade for dealing with all these commands. So the command stack would have functions such as undo, redo, and execute. And execute will be whenever we create a new command. And it will handle all the commands and keep track of them, knowing which order they were executed. The command is an interface that has, for instance, execute the first time we execute, perhaps an undo to undo the command, and redo to execute the command again. And of course, I should draw in the association where the command stack holds the set of commands. As someone that is providing functionality to Eclipse, I will have to create concrete implementations of the command. So for example, I could create a cut command, and I would have to implement the execute, undo, and redo. And then, of course, inside this class, I would have the behavior that would keep track of what was selected, make sure that it gets on the clipboard, but also know what action to take to undo the cut if that was required. Of course, in Eclipse, there are many of these commands. Commands like drag and drop, maybe a refactoring command that can undo itself also. There are a couple of other interesting things in here, but you see the point. What we have done is we have taken something that is typically an algorithm and a function and encapsulated it into an object. In this case, for the purpose of being able to attach commands, perhaps to menu items, to do things like undo and redo and so on. Before we conclude this pattern, let me make sure that we know the vocabulary used in the design patterns book. In the design patterns book, they talk about the command as being the interface that we've discussed. And then we have concrete command, which are obviously the implementations of the command that holds the actual algorithm that we want to encapsulate. This concrete command may be doing something on a receiver. So in our case, maybe we were talking to the clipboard. We have also the invoker, which is a client of the command that typically does not know exactly what is being executed. They just know that at a certain point in time, maybe on click, maybe on selection of a menu item, the command needs to be executed. And we use polymorphism to then select the correct algorithm.
In this section, we'll take a look at a pattern called template method. The template method is often used in the context of building frameworks or reusable code structures. What we'll do is we'll first take a look at template method in code. I'll show you the problem and I'll also introduce a solution for you. I'll draw it out for you and we'll have a little discussion around this whole refactoring, and then we'll abstract it and summarize the template method pattern.
To show you the template method pattern, I've prepared a little example. It's a trivial example, but I'll go through it class by class. Let's start by explaining the main method. The main method I've split into two. The first part just creates an instance of a query. The query we'll see is an interface. The query people is an implementation of that interface. And then I have a little utility method that executes the query. If you look at that method, all it does is execute the query, gets back some result, and then I created a dummy method on the result that prints out whatever comes back from the query. And if I execute this program, all it does is print out the result. In this case, 4 people, John, Jim, Jill, and Steve. The output here isn't all that important, but we'll study the implementation. So the query is an interface, and it has one method execute that returns a result. I've created an implementation of that interface that I call query people. It has an algorithm, and it's this algorithm that is actually interesting. The algorithm starts by opening a connection. Again, I've created a dummy connection, so I'm not hooking up to a database in case you want to execute this. It should be a little easier for you. And then I execute that query upon that connection, and then I get back some result. And then finally, I close the connection and return the result. Now let's assume we want to create another query that can be used from main. And this query would be on companies. Now, how different would that query be? It probably is so similar that the natural thing for a programmer to do is to do a copy and paste. So I'll copy the query people, create a new class that I will call query companies. The implementation should be very similar. So I'll open up the query companies and just change people to company. Test this out by creating a new instance of the query companies query, and then execute that query. If we now run the program, we now see that we're printing out both the people from the first query, and now in a different query, we're printing out the companies SciSpike, IBM, and Microsoft. So we have 2 implementations of query, and perhaps we expect hundreds of those. But let me put them side by side so we can compare them. The 2 algorithms are almost identical, apart from a little piece in the query string, where we have changed company to people. The template method pattern would allow us to extract the commonality in these 2 algorithms. What we will do is to introduce a new implementation, which I'm going to call abstract query, that implements the query interface. And I will try to implement as much of the algorithm as I can in the execute method of abstract query. I'll start by simply copying the algorithm from query people. Most of the algorithm would be common for all queries, but notice that I can't formulate the query string. In the template method, we solved this by declaring a method within the abstract base class that declares what we need the subclasses to do. I'm going to create a method here called getQueryString. Notice that the method is abstract and protected. This, of course, also means that we have to make the class abstract. Only thing I need to do now is to remove the query string from the abstract class, and call the getQueryString on the subclasses. That effectively means that we're doing as much as we can in this abstract class, and then we delegate to the subclasses to formulate the query string. Now that we have introduced this abstract class with the algorithm that we want to apply, we need to go back to the concrete queries and refactor them. The first thing to do is to make sure that instead of implementing the query, that they extend the abstract query. I'll let Eclipse generate the getQueryString method, and then I can copy the query string from the execute method into the getQueryString method. Finally, we can delete the execute method that we no longer need. And we should do the same change to the query companies class also. And by doing this, we've removed the duplication of algorithm between the query companies and query people. The special versions of each query now only have the production of the query string. Everything else has been lifted up to the base class so that the algorithm is the same for any query that we might introduce in future. Of course, in our example, the algorithm was quite trivial, but you can imagine there could be all kinds of new things that happen in the framework. Maybe we need to throw some exceptions or catch some exception. Maybe we need to deal with connection pools and so on. And what we effectively done is we put all that policy of how to execute queries in one place, rather than having it spread out across all the concrete queries. And if we execute it, we will see exactly the same result, which was expected. All we've really done is refactor it and made the code a lot cleaner and made it a lot easier for developers to introduce new queries.
So let's take a look at the pattern and try to abstract it a little bit, and I'll draw you some pictures. The concept here is that we have some kind of interface with some method on it, or maybe multiple methods, but I'm just going to create one called M. Unlike most of the other patterns where we've been trying to hide something from the client or make things easier from the client, this pattern has nothing to do with the actual relationship to the client. It's more of an internal refactoring pattern. So like we had in the example that I showed you in code, let's assume that we have a couple of implementations of this interface. Let's say implementation A and implementation B, and they both implement the method M. And what often happens in an application like this is that when we studied the implementation of M in various implementations, we find that the implementations are very similar. So in this pattern, what we're trying to do is we're trying to make it easier for developers to create new implementations of the interface. And the way we will do that is that we will try to take the algorithm, analyze it, and try to figure out what's common across the various implementations. So perhaps we look into the method of implementation B and we see that it has a set of steps. And we could probably analyze those set of steps and maybe even build some kind of flowchart. So say, for instance, that we analyze it and we find that this algorithm has 3 phases. There is a setup phase, there is something very unique to implementation B, I'll just call it doX, and then there is a teardown phase. We may not see it immediately, but it's when we're studying the various implementations that we will see some kind of algorithmic pattern. Perhaps when we study implementation A, we see that we do the same setup, we do the same teardown, but instead of doing X, we do, say, Y. When I created the code example, that manifested itself by the fact that I had to copy and paste code from one class to the other. This is a very typical indication that a template method might be a good way to go. We need a place to implement the commonality between the various implementations, so we introduced an abstract class that implementation A and B in this example would inherit from. That implements the interface that the client expects. And now it's a matter of taking the algorithm for the method M, take it from one of the classes, and lift it up into this abstract implementation. In this trivial example, the setup and the teardown can remain in the abstract implementation. However, the doX has to be wiped out. We have to do something to invoke the subclasses at that point. What we're doing then is we're ensuring that setup occur before teardown, but we can't do whatever is in the middle in this example. because it has to be done differently for the various subclasses. So what we'll have to do is we have to, from within the implementation of M on the abstract implementation, call some method that we introduced on the abstract implementation, say doIt. It's typically protected because we don't want the client to be influenced by this. This has nothing to do with the interface to the client, but it would be something that the subclasses perhaps must or can implement. We can now change the various concrete subclasses, here implementation A and B, and just introduce the doIt method. So they will not be responsible for the setup or the teardown. All they have to do is to implement some plugin method, that's why we call it a template method, that will be called from the base class. Now, some people have called this the Hollywood way of doing object-oriented design. Don't call us, we call you. So in this case, it's the framework calling the application code in many cases. A more common way is, of course, that the applications have been using libraries from the framework. I would also like to throw out a little bit of a warning here. I've certainly seen a lot of framework overusing this pattern. Overusing it to a point where it becomes very, very difficult for their client, being the ones writing the subclasses, to use the framework. Often there are so many methods that could be implemented or could be overridden, or some that must, and often they have rules where if you override this method, you must call this superclass method before you do something, and it becomes very complicated. There are several famous companies that come up with some framework based entirely on this principle that has been a total tragedy. Before we end this session, let me bring you back to the Design Patterns book and some of the vocabulary. In the examples that they would show on template method, you would have the concept of some abstract class that has a template method, and the template method would have an algorithm, some kind of policy that you want enforced at that level in the hierarchy. It does something that should be common for all concrete classes, but then it calls method upon itself, often abstract protected methods, that then will be implemented by the concrete classes. And this makes up what we call the template method pattern. Template method is a very common pattern, mostly used in frameworks. A couple of places where you might have seen this in the Spring JDBC templates, where Spring implements as much of the database logic as it can. But as a programmer, we have to provide something. For instance, we might have to provide the query or the way we extract data out of the database. Another is the JE servlets, where the base servlet parses all the incoming requests and call the do get and do post upon itself that you as a programmer would override to create the concrete servlet that doesn't work. And of course, if you don't care whether you come in with get or post, you can also override do service on the servlet. So you've probably seen this implementation technique before. And now you have a name for it called template method. In this section, we will cover a design pattern called strategy. I would put strategy as one of the fundamental patterns. It's certainly one of the most commonly used patterns. The way we're going to approach this is introduce a strategy problem. I'm going to do that with drawings. And then I'm going to show you how to solve a specific problem using strategy. And also, we're going to spend some time implementing this in Java. And finally, I'll abstract it and summarize the strategy pattern. Sometimes we build objects that are quite complex, and often these objects have a set of independent concerns that they implement. Let's say we're building a printer. A printer can be a very complex object that implements multiple concerns. For example, one of the concerns of printer is to queue the jobs and prioritize them based on whatever strategy that we may have for queuing. Another concern that we may have to implement is the notification of users. We may also need to keep track of users and who have access to various things, so some kind of user management. there are several independent concerns being implemented by a single printer. The strategy pattern gives us a chance to separate some of these concerns and break them into what we call strategies. Before we dive into the pattern, let's take a look at some of the mistakes that designers sometimes do. Often what they do is they expose this complexity to the client by adding multiple implementations. We might, for instance, ask the user to use a printer queue to add the element into that, and then maybe later on register for completions of job by the printer in a different place. Now, the user really sees this object as a single object, and the fact that they have to deal with multiple elements or multiple objects to deal with their jobs or to get the printer to work is an additional complexity to the client that they don't appreciate. So the client wants to see a single printer, but we, for implementation reasons, want to break the printer into pieces. One of the golden heuristics of object-oriented design is to always reflect your client's view. So we will let the client have a single object, the printer. We will still split up the printer into pieces. We would just hide that from the client. Now we'll start by taking an example of the printer queue. I'll break up the printer queue and put it into a separate object that we're going to call a strategy. Printer will know that as a print queue, and it will use this object behind the scene through a well-defined interface. And the key for this to work properly would be that it is hidden from the client and it does not introduce any new complexity to the client. In other words, the client's idea of what a printer is not compromised. The strategy dictates that we come up with an abstraction for the orthogonal concern or the independent concern. Perhaps here just queue or print a queue that would have things like add, remove, and get first job in the queue. The interface defines the strategy, and we can have multiple implementations of that strategy. For instance, a simple FIFO queue or first in, first out queue, but any other variations on queues would be possible. So notice a few characteristics of this solution. The client is not impacted at all. They are using the printer. The printer internally breaks out a part of its responsibility into what we call a strategy. It defines an interface for that strategy that defines the abstraction, and it may have multiple variations of implementations of that strategy. And the printer will forward to that concern or the strategy whenever it's responsibility to do some part of the job that is conceptually the responsibility of the printer. Let's take a look at the printer example in code. I'm going to open up Eclipse again, and I have a little prepared example that we're going to start from. Let's start by taking a look at the printer, and let's take a look at where in that printer we implement something related to queuing. As we look through the code, we see that in multiple places we are dealing with the print queue and the priority and how to get to the job. So for example, in this run method, we're calling get next job and remove job. We have a private method that gets the next job. We have another private method that removes the job. In addition to dealing with the queue itself, we obviously have the other jobs such as printing it, which is doing some translation and dumping the content onto a printer. And we have also other methods like, for instance, something that converts the content of the job into some printer language, and so on. As we can see, the printer is implementing multiple concerns. What we want to do is to break out that queuing, but we'll do that later after we run through the example. I'll open up the main class, which is a simple test driver, and then we'll examine the code and explain what's happening. The first thing I'm creating is just a simple random object that I'm going to use later. And then we have a set of users that I've created. This is so we can simulate the jobs. I create the printer that I then start. Printer is a subclass of a thread, so I have to start it. And then I'm iterating through in a loop and creating jobs and picking a random users, setting some random content. And then finally, after we've created 10 jobs, then I'm basically shutting things down, and it forces me to wait for a little bit until all the jobs have been printed. I want you to notice in main here that the client's job is very trivial. They have a simple printer, very simple interface, and they're not bothered with the fact that there are multiple queuing strategies, that we have to translate things into printer languages and so on. It's a simple printer. All they need to do is add a job to it and ask the printer to print something. Before I run the code, let me just explain the code here. The first thing was that we in the loop are calling this print method. If we go into this print method, we will see that this simple print method is basically just adding the job that we created onto a list that is called jobs in the printer class. When the job has been put into this list or this queue, the run method, this is where the main algorithm is. While we are supposed to run, we go and we sleep a little bit, and then we pick up the next job. And if one exists, then we will print this job and then remove the job from the queue. Finally, we'll inform the user if the user is listening to something, if the user want to know when the job is done. If we now run this code, we should see on the output, the printer is accepting the jobs and then printing it out. So let's run it, and then we'll see the jobs being printed out. We can see they're being printed in order. It might look a little weird, but what I'm doing just to translate the actual content is I'm uppercasing it and then printing it out in reverse just to do something interesting. Now let's implement a strategy. And what we'll do is we'll break out the queuing behavior. And I'm going to start by creating a simple interface. And we'll call this interface for a printer queue. And a printer queue will be the abstraction that I want to separate out so that all the queuing behavior is in one place. So we need to define that queuing behavior. Perhaps we'll have a couple of methods, an add job method, and perhaps another method for getting the actual top job or the first job. Maybe it could return a job, and then we'll get next job, and that could be the abstraction. Now we should document this and write a little bit of comment for it. So I'll write a comment for the add job and just say that adds a job to the printer queue. Then for the get next job, which might be a little bit more interesting, here we could say that we get the top job, and if there are no jobs, we could return null. So that completes our abstraction of a strategy. So now we have a queuing strategy that we want to extract from the overall printer implementation and put into a separate hierarchy where this printer queue is the interface or the abstraction of the concern that we're breaking out into a strategy. So before we start refactoring the printer, we need to create an implementation of this printer queue. I'll create a simple class that I'm going to call simple FIFO printer queue or simple first in, first out printer queue. I'll create a simple variable that I'm going to call queue, which is of type job, and we'll use one of the Java collection classes for that. Maybe something simple like linked list. We'll need an implementation for the add job method. Go to the queue and add the job. And for get next job, we could do something trivial like go to the queue and remove the element. The queue could be empty though, so we probably should first make sure that the queue is not empty and only then return the element that we removed. And if the queue is empty, we should return null. Come to think of it though, it would be simpler to use the pull on queue, which has this exact implementation. The pull operation on a queue returns the first element or it returns null if there are no elements. Now that we have an implementation of a queue, we should be able to go back to the printer and refactor it to use this queue. So let's first introduce a variable that we're going to call the printer queue, which will hold an instance of a simple FIFO printer queue. I'll remove the jobs variable so I'll see where the errors pops up. I can obviously remove the construction of the jobs variable from the printer constructor. We see now that we removed the jobs variable that we've introduced a new set of errors, and we should go and attack those. To get next job, we could simply just go to the printer queue and get the next job from the printer queue. We can delete the remove job method as we have a new behavior for the printer queue that does that for us. And we can quickly refactor the algorithm for printing the job too. We could basically have the job returned from the printer queue. We could remove this. After we've done that, we can actually get rid of the getNextJob method also. And it seems my final error is in the print method, where we need to change to use the printer queue. And that concludes the refactoring of the printer. This made the printer a little bit simpler, and we now have a implementation of a printer queue that has been separated from the printer, but is still hidden from the client. Well, let's make sure that the new printer works. So I'll go back to main and run that and see if we get the same result. And it looks identical to what we saw before. We get the jobs printed in the order that they were produced. One of the strengths of the strategy pattern is that it's now relatively easy to introduce a new queuing behavior for the printer. We can do so without affecting all the other implementation of the printer. And to do this, I'm going to make an extended example. Maybe what we do is we have a queuing strategy that is based on the priority of the jobs. To do so, I would have to add priority to the job so we have some chance of organizing the jobs based on priority. So I'll start by going into the job and adding the concept of a priority. I'll create a simple property called priority of type int, and I should probably give that a default priority of 50. We should probably introduce a method for grabbing the priority, so a getter for priority. And we should probably also introduce a constructor that allows the user to set the priority at construction time. We have 2 constructors already, so I'll duplicate them and create 4 constructors, one with priority and one without priority for the 2 constructors that we already have. So now jobs are allowed to have priority. Now we need to take that into account when we create the jobs and also when we print them. Let's start by creating a printer queue that understands priorities. I'll create a new one by copying the FIFO printer queue and simply call it job priority printer queue. I need to change the queue variable now to be of type priority queue. We don't really need to change the variable type. That could still be a queue since priority queue implements the queue interface. For the priority queue to work, we need to take into account the actual priority of the job. And the easiest way to do that would be to create a comparator that we pass on to the priority queue itself. So I'm going to create an anonymous in a class here that is of type comparator for jobs. And in the required compare method, I'm simply going to forward to the integers compare. And that should allow us to prioritize the jobs. Now the priority queues should use this comparator and compare 2 jobs or put them in the order of the priority. Before we can test this out, we need to go back to main and inject the priority into the construction of jobs. So I'm just going to use the random and ask for the next int up to 100. So if we run it now, we should see that the jobs come in a different order potentially from where they were created. We'd be extremely unlucky if we managed to print them in the correct order. Another thing we need to do is obviously to instantiate the priority queue inside the printer. So we'll do that real quick and replace the old simple FIFO printer queue with the job priority queue. Okay, let's run it and see what happens. Okay, so we go back and run the same example again. And let's take a look at the console. And we see now that the jobs come in what looks like random order. It's not random, obviously. It's based on whoever got the lowest priority. And that's exactly what we were aiming for, so that looks good. So we changed a single line in the printer implementation, and it changed the behavior of the printer queue. And notice that we now managed to separate out the concern of prioritizing the jobs and queuing the job into this so-called strategy, which we now call a printer queue. I could imagine breaking out other concerns also into strategies into the printer. Maybe the translation from the content string into a printer language could be a strategy. Maybe the notification or the way we notify our users could be a strategy, and so on. but I'll just stick to this simple printer queue because I want to illustrate a couple of other issues with strategy using that example. One common concern is who creates the strategy. In some cases, we might want to let the client define the strategy. That is, we want the client to instantiate a strategy for queuing and pass it on to the printer, so the printer is totally unaware of the various implementations of the strategy of queuing. So what we could have done is we could refactor the printer so that the printer allowed for a constructor where a strategy could be passed in. We could have the queue strategy being passed into the constructor. I'll leave the old constructor and let that create the simple FIFO printer queue. And I'll implement the second constructor that allows the client to pass on the queue strategy. Let's just fix the variables. Let's comment out the printer queue. Well, we need to introduce the empty printer queue. So that should do it. If we run it without changes to main, we should see the simple FIFO print queue take effect. And it looks like that is working just fine. But now we can go back to the main method and let the client introduce a strategy. And we can have the client introduce the job priority printer queue. And if we run it again, we should now see that the client controlled the printer queue. And we're now getting jobs printed out in priority order. Now, in many cases, letting the client instantiate the strategy and passing it on may be too much. We may want to control the implementations within the printer hierarchy, but we can still use this implementation method like called strategy and give the client some freedom to define what queuing strategy to use, but perhaps control that by using something like an enum. So let me show you an example of that. What I'll do is I'll go to the printer class and I'm going to introduce an enum, which I'm going to call queue strategy that has two values, FIFO and job priority. And this is the only thing that I'm going to expose to the client. Instead of having the client passing on an object, what I'm going to have them do is to pass on an enum value that specify which one of the queuing strategies they want me to use. With that, I can control how these enum values map onto underlying implementations. So now I can still have the queuing implementation controlled by the printer hierarchy and hidden from the clients, and just make a simple abstraction to the client where they're allowed to pass on one of these enums that maps onto one of the underlying implementations. While I'm in here, I should probably also fix the default constructor and take advantage of the mapping that now occurs in the constructor that takes an enum. Notice that we now still allow the client to control which queuing strategy we use, but they have a much looser coupling to the actual implementations of strategies, which in some cases can be much more desirable. I'll just quickly fix main here so that it uses the enum rather than instantiated strategies. And let's also run it to make sure I didn't do any mistakes. So if I execute it, we should now see that we pick the job priority, and that looks good. We see the order is based on priority, not in the order that they were received. And I could, of course, also change this back to FIFO and then run it again and make sure that it works that way too, and that looks also good. Clients were able to select what strategy we should use for queuing, but we kind of hidden the mapping of that to the underlying implementation. Sometimes that's desirable, sometimes not. Then there could be different variations. It could, for instance, be that the printer changed the strategy itself based on, say, time of day. Maybe we have a different strategy during night where we do the longer jobs, and during day we pick the smaller jobs first. And that could be entirely hidden within the printer. And maybe our only goal for the strategy was to be able to separate out that concern to clean up our implementation. So let's finally summarize the strategy and make sure that we know it at a slightly more abstract level. So the problem is that some objects may become very complex and implement multiple concerns. And sometimes it's desirable to partition the object into multiple objects, each implementing a single concern.
However, we have to be careful so we don't introduce complexity to the client. Sometimes the concern may have multiple implementations that we also want to swap at runtime, either controlled by the client or perhaps controlled by the context of this complex object itself. The solution suggested in the design patterns book is that we partition out the concern that we want to implement separately into what's called a strategy. We define a well-defined interface that formulates the responsibility of the strategy. We may have multiple concrete strategies or implementations of those strategies. And we have the original object in the pattern called the context. And when a method on the context is called, it may delegate some part of that responsibility to the strategy. While we implemented this in Java, I showed you some variations. In some cases, the client instantiated the strategy. In some cases, the context itself defined the strategy. And there could be some combination there. A very common way to implement it, for instance, in Java, is to inject the strategy itself. We finally come to the last section where I'm going to try to wrap up the whole design patterns in Java course. We'll take a look at some of the missing patterns I didn't cover and why I didn't cover those patterns. I'll mention some of the Java implementation constructs that may change the way that you might implement some of the patterns. And I'll recommend some things that you ought to read up on to become more fluent in design patterns. The Gang of Four book on design patterns covers 23 different patterns. In this course, we only covered 15 of the patterns. Some of the missing patterns are in the catalog of structural and behavioral patterns. We actually covered all of the creational patterns in one big swoop, but we missed out in the structural patterns bridge and flyweight. And in the behavioral patterns section, we missed out chain of responsibility, interpreter, iterator, mediator, memento, and visitor. Let me quickly discuss some of those patterns and perhaps also why I didn't cover them. In the structural patterns section of the Gang of Four book, we have the pattern called bridge and flyweight. Now, bridge is about how you separate interfaces from implementation, where you design an interface between maybe two sectors of your implementation or two sections of your implementation, and you define an interface that shows how these two sections interact. Now, I didn't cover that pattern simply because it hasn't really become a pervasive use of design vocabulary, in my opinion. Flyweight is a strategy to extract common information between a set of smaller objects into a single abstraction. This is often used to save memory. It's a very practical pattern in the cases where this is useful, where you need to save this memory, but it's also not a very pervasive pattern, and that's why I decided to skip it. I also skipped quite a few patterns in the behavioral catalog. Chain of responsibility, I was thinking I should include. However, again, it's not that commonly used, but it's all about delegation, where you use some natural structure of object that you change together so that when something happens in one object, you can propagate or escalate or delegate, if you want, some request through this chain to find the appropriate handler. It is actually a fairly practical pattern. I would recommend you read up on it. It's used a lot in user interfaces for doing things like context sensitive help, for instance, but I would recommend that you read up on it. The interpreter, on the other hand, is a pattern that works in a very small domain. The idea here is to build a parser that uses the natural class hierarchy that makes up the language being parsed. And you can see this being used in parser tools such as Antler and so on to do parsing. It's very rare that someone is building this without some parser tool. So I decided to skip it again because it's not very widespread. The iterator is a very commonly used pattern. It's a pattern where the algorithm to access a collection is abstracted away from the client to make it easy to access various implementations. So, for instance, you can access a tree structure the same way as you do a linked list or an array. The mediator is a pattern used quite often in user interfaces, and you have actually patterns that are built up around that.
things like model view presenter and so on, where the model and the view is being mediated by the presenter. Memento is a nice pattern. The idea here is to have a client hold a state on behalf of a service that is naturally stateful. This is what we often do in web world by using things like cookie, for instance. It's a very practical pattern. It's probably going to be a very important pattern in the world of massively scalable systems, where the client is holding some information that they will pass back to a stateless service so that that stateless service can read where they were at the last time the client connected. Visitor is a very interesting pattern, one that is very often misunderstood and very often overused in the places where I see it. The idea of a visitor was basically to solve something called multi-method or multi-type dispatch. So this is when you have an algorithm that depends on more than one type. It's a very commonly misunderstood pattern. It's one that is an intellectually challenging thing to learn. So recommend that you read up on that one. One thing that is interesting when you read up on all the other patterns that I have covered is that Java has very specific issues in the way you implement it. Now, there are things that weren't commonly available when the Gang of Four wrote the Design Patterns book that you may want to take advantage of. So we have things like reflection, for instance, in Java, which allows you to get to the class or get to some of the metadata behind objects. And that can often be used very effectively in creation. You have things like dynamic proxy, which is a very interesting way of implementing some of the pseudo delegation patterns that we mentioned in one of the chapters. Dependency injection, also common, particularly when it comes to things like Singleton, for instance, that could be a very useful feature. And you have things like Aspect J, which is very, very powerful and allows you to do a lot of interesting things around things like proxies, but also mediation and creation of objects and so on. So that's another interesting Java specific issue that you might want to take into account. And also Java 8 introduces things very close to the concept of closure. And also things like aspects are almost back into the language in Java 8. So there are a set of very specific Java implementations that you want to take advantage of when you implement some of these patterns. The main source for the reading should be the Gang of Four book, the book called Design Patterns, Elements of Reusable Object-Oriented Software, as depicted on the right-hand side. And I would recommend to learn all the patterns in that book. It defines the main vocabulary used in design, and it's the original source. Now, some people find the book extremely abstract and hard to read. I think what you need to do is to break it up and study one pattern at a time, but I'll come back to that later in this section. I wanted to mention the Head First book on design patterns. It's easier to read, a lot more graphics in it, and it has some code examples that might be useful. Take a look at it in a bookstore and see if that suits your style better. So I decided to pick this book by a guy called Trygve Renskaug, who is a Norwegian computer scientist working with objects. It is unfortunately out of print, but you can, if you search on his name, Renskaug, working with object, you can find his manuscript that he has put out as a free PDF version. What's interesting about this book is it makes it very easy to describe patterns. His treatment of roles is very interesting. I was once working with a tool that he created that unfortunately is no longer available. It was a tool based on the method called ORAM, and I found it extremely useful in the way I want designed and also the way I apply pattern in a practical world. So I would actually recommend this book very much to understand how to synthesize patterns together. When you pick up one of these books and you want to study the patterns and learn these patterns, I would highly recommend that you do that in groups. I like brown bag lunches. I used to do that with my employees to learn how to apply the patterns. We used to do one pattern at a time, and we used to pick someone to read up on that pattern, study it in detail, and then explain it to the group. And then we would discuss where and if a pattern may be applied in our domain. We tried to contrast the pattern being discussed with other patterns that we had learned. This is a very efficient way of learning patterns. I would highly recommend it. I want to get back to this concept of if a pattern should be applied. And I want to do that with a short story that I'm going to draw. There once was a kingdom where the king had 4 heirs. And what the king was afraid of is that once he died, that these 4 heirs would start arguing. His kingdom was of a geometric shape that looked something like this. Now think of this as 3 perfect squares put together. Now the king has summoned you to solve this problem, and he knows that his heirs will start arguing over the land and maybe go to war unless you can figure out a way to split his kingdom into 4 pieces. And these pieces have to be consecutive. So no open gaps, no fragmentation. This turns out to be a problem that isn't all that easy. If you think about it for a long enough period of time, you would actually solve this one. The solution to this is basically to split it in a way, something like this. And now you get 4 pieces of equal size, shape, and all consecutive. Now this problem is really just a warm-up. The harder problem that I wanted to show you was one in which we changed the parameters a little bit. In this case, we're going to have 5 heirs, and we need to split it into 5 pieces, say a different kingdom, a different king. This king has a perfect square as their kingdom. Now, how would you solve that? Now, of course, the solution to this problem is very trivial. And if I had given you this problem first, you would have had no issues. The solution is simply just divided into 5 vertical or horizontal. So what can this exercise teach us about pattern? What I've found to be the most common mistake when people are using patterns is that they're overusing the patterns. You know, the classical thing, the one with a hammer tends to look for problems involving nails. This is what we need to try to prevent. When I give someone that has just learned a set of patterns a problem, they look for places where they can apply that pattern. And that's good as a mental exercise, as a learning exercise. However, it often complicates a design where there is a very simple solution available to you, a very trivial one that anyone can understand. Some designers tend to say, well, we could do that by using X pattern and combine it with Y pattern. And they create a structure that is overly complex. It is the most common problem I see. So patterns are great, but they have to be used when you have a problem to solve that matches the problem description of the pattern itself.